Good morning, everyone. I welcome you all for the day 4 session of the VLSI design program. For this, we have our expert, engineer Arun Vadhana is with us. He is going to deliver lecture on digital simulation design. He is presently working as a VLSI application engineer in Interpol Technologies, Delhi, and he has received his BTech degree from YMCA University of Sciences and Technology in Electronics and Communication and MTech from NIT Kurukshetra in VLSI design. So I invite Engineer Varun to engage the session, please. Engineer Varun.
Okay, we start. Okay, thank you, ma'am, for giving me an opportunity to present this topic in this VLSI design program. So, first of all, a very good morning to all of you. Uh, my name is Varun Badana. I'm from NTPL Technologies, headquartered in Bangalore, and we are the authorized distributor of the Cadence product across the India. And the main areas in which we deals are VLSI design, wireless and communication, embedded system, power electronics, PCB design, motors, drives, and controls. So we are always focused in bringing out the cutting edge technologies from all around the world to the Indian academia with the thought of bridging the gap between industries and academia. So we used to organize trainings, workshops, FDPs, and we also offer the internships program to BTech and MTech students. So today we have an agenda to discuss the complete VLSI flow using the Cadence EDA tools. So first of all, we will start with the design methodologies that are being accepted in the various VLSI industries. So basically, there are two type of design methodologies. First one is full custom design, and the other is semi-custom design. So what does this full custom design mean? Uh, in full custom design, we start our circuit right from the scratch, from the transistor level, and it is very if you consider the advantage of this full custom design, it is very we can increase the chip performance as well as we can reduce the layout area, because we are working in the layout design manually. We have to design the layout manually. So if you will see the feature of this full custom design, it is actually a slow process because we need to proceed with that from the transistor level, right from the scratch. So this process is preferable if you want to fabricate your design in a bulk, in a volume. If you have to produce your IC in volume product, then you need to follow this procedure. And coming to the advantage of this, it is very less prone to error, as well as we can achieve the maximum circuit performance in this design methodologies. Now coming to the semi-custom design we adopt when we are having some standard cell libraries. Suppose our half of the design is ready with the standard cell library, so we are going to use those standard cell libraries using the synthesizer tool. So those synthesizer, depending on a RTL, it will generate a gate level netlist that we are going to discuss while having the tool demonstration. So you can see here, this is a standard cells of 5 input standard cells. So this is a width of the standard cells WP. This WP is a width of the PMOS device we are using in an active area. WN is for NMOS. So coming to the advantage of this semi-custom design, suppose you want to produce your product in a very less amount of time, so this method is preferable because you need not to start your circuit right from the scratch transistor level. Your half of the design is already done, that are being supplied by the fabrication industry in the form of standard cell library. Only you need to do the placement and routing. Now if you will compare this graph, this chip performance versus the time in design, so the time to market taken by this full custom design is more than the semi-custom design, but at the same time you can achieve, there is more opportunity to increase the circuit performance in case of full custom design. Now coming to this flow, ASIC stands for application specific integrated circuit. When you want to fabricate a IC that is specific for a general purpose, like you want to fabricate a IC for washing machine, for some particular cell phone. So these are specific for some particular application. So we need to approach in this flow to fabricate that IC. So first of all, the first thing that comes to your mind while designing a chip is the specification, design specification. It can be your maximum power supply on which your chip is going to work. It can be the delay. It can be the temperature conditions, the environment. So these all include in the specification, design specification. So after this design specification, it has to be converted into the behavior description. So that behavior description will describe you describes the functionality of each and every module you are going to use to implement the entire chip design. So that behavior description has to be converted into the RTL description in the form of HDL coding, that is hardware description language. You can use a VSDL, Verilog, anything you want to use. After that RTL coding, you have to functionally verify your code. The step is called the functional verification, functional simulation. So the tool we will use for the functional simulation is Incisive. The Cadence is offering a tool named Incisive. Now after the functional simulation or functionality of the chip is verified, we need to synthesize it. Actually, what happens, suppose we have written this line. Okay, suppose I want to design a counter IC. So in the Verilog code, I have written this line. This is the behavior of my code, not a gate level functionality. So this synthesizer have to synthesize my this code into gate level modeling. That is a hardware netlist. So the output of the synthesizer will be the gate level netlist, and after that we need to perform the timing simulation. So there is a difference between functional simulation and timing simulation. Functional simulation will just check the functionality. Suppose adder, let's take example of adder. So functional simulation will take care whether the 3 bits are added or not. It is not concerned with the after how much time it will get added. But in the timing simulation, you will get the delay information also. Now the next step is DFT. DFT stands for design for test. You need to make your chip testable after it got fabricated. So you need to insert some scan in, scan out signal so that you can find faults in between the chip after it got fabricated. So this was all about the front end work. Now coming to the physical design. So the first step in the physical design is floor planning. We need to plan the floor where our standard cell are going to be placed. So this is a very important step to predict our budget of the chip area. So after this floor planning, we need to go with the power planning. Power planning stands for we need to run the VDD and ground rails in our design. Okay. So after this power planning, we need to do the placement. Placement stand for I need to place all those standard cells that have been called by the synthesizer from standard cell library. Okay. Now after this placement, next step is CTS. CTS stand for clock tree synthesis. So why do we require this step? Suppose this is your circuit. This, this is your launch flip flop and this is your capture flip flop. Okay, and in between you have a combination logic. So the main important things while designing a digital circuit is a clock, because you need a reference at what reference you want to perform the operation. So we generally take a positive edge or a negative edge depending on the conditions. So we need to make sure that each block in your design should get a edge, positive or negative, at the same instant of time. But when we see there is some wire delay in the design, you will see these two block will not get the clock at the same time because there will be some wire delay. Suppose launch clock is getting a clock at T1, so captured clock will be getting a clock at T1 plus delta T. Okay, so if the combinational logic is sending the data at some time between T1 to T1 plus TT, capture flop will fail to capture the data. So we need to make sure that both the flop are receiving the clock at the same time. So these all steps will be taken care by the CTS step, clock tree synthesis. After this CTS, we need to perform the routing. Routing stands for the actual layout step in the digital design. We need to connect the standard cells with each other. So after the routing of physical circuit is ready, we have implement of physical circuit on a chip. We need to verify it. The step is called the physical verification. It includes two steps, DRC and LVS. DRC stands for design rule check and LVS stands for layout versus schematic. So why do we need to check these DRCs? Because these are set by the fabrication industry. They should not be violated. There are some minimum dimension which we need to follow while designing the layout, so that we can design a verified chip design in a minimum silicon possible area. So the main aim of these DRC rules to optimize the area in the chip. The next is LVS. LVS stand for layout versus schematic. So this step will check the connection of your layout with the schematic, whether it is meeting or not. The next, we need to extract the parasitic components that is existing due to the metal layers or polysilicon layer in the layout. So we need to extract it and back annotate it to perform the post layout simulation. And lastly, the tool will give you the GDSII, that stands for graphic data stream information interchange. That is a binary file to the fabrication industry. So it will contain all the mask information, all the metal layers information, how the metal layers are connected in your design. So depending on that binary file, the fabrication industry will going to fabricate your actual design. So after this flow, we can start the demonstration for some design. I will take an example of a 8-bit up-down counter. We will write down the Verilog code for the 8-bit up-down counter, and we will generate up to the GDS file. So it will take some time to open. So if so the tools we will use for the functional verification is NSYSIV, and for the synthesizer we will be using RTL compiler, and for the entire physical design from floor planning to the routing, the tool will be used Encounter. Encounter is the tool name. Then for the physical verification, we will use Assura tool. The base platform for this tool is running for the is Linux. It will run on the Linux platform only. So
जी सर हाँ
so here I'm having my already written Verilog code for the counter. So here you can see it is a 8-bit up down counter having active low reset signal, and M is a control input. Depending on the value of M, it will behave as a up or down counter. For M equal to 1, it will increment its count, and for M equal to 0, it will decrement its count. So this is just a behavior description of my counter RTL code. I have not specified how the gates are connected. I have just specified the behavior of my code. So I have written a test bench for the same. So from the test bench itself, I am instantiating my top module counter, and I'm creating the clock signal using always statement. So what we are going to do, we will simulate this Verilog code, and we will check the functionality of our Verilog code, whether it is behaving as a up down counter or not. So there are some commands to invoke the tool. Okay, so these two codes are ready for the simulation. So before the simulation, you should know the steps how the simulation occurs. So it occurs in 3 steps. First one is compilation, second one is elaboration, third one is simulation. So in the first step, we will just check the syntax error in our code, whether there is a syntax error or not. So all the syntax error will be taken care by the compilation step. The next is elaboration. Elaboration will set the design hierarchy from top modules to bottom modules and will connect all the signals. The last we will perform the simulation. So this option is for compilation. We will select our Verilog code and then compile it. Then next we need to compile my test code. So in the work lib, I will compile my top module, that is test bench, from the because from the test bench itself I'm calling my counter, and I can simulate this. I can send this all the signal clock count M and reset to the waveform window. I can simulate this like this. So you can see until the reset is 0, your count is at a 0 state. After reset become 1, your count output is incremented at each positive edge of the clock. Okay. So for M equal to 1, it is incremented, and for when M becomes 0, the counter is decremented 0D, 0C, 0B, like this. So in this way, we have checked the functionality of our code, right? Next step is we will synthesize this code into a gate level modeling. So we can close this. we can find out the code coverage also in this tool. What we mean by the code coverage, how much the main code has been exercised by the test bench. What are the numbers of what are the number of possible input vectors that have been covered by the test bench. Okay, I will give you example. Suppose you have written down a Verilog code for a OR gate. Okay, it is having A, B as an input and Y as an output. Okay, so suppose in your test bench you have taken two case only, A equal to 0, B equal to 0, A equal to 1, B equal to 1. So the total output cases for the two input is 4, but in your test bench you have covered only two cases. So your code coverage is 50%. So we have to make sure that our code coverage always should attain the value of 100%. It cannot attain 100%, but it should approach to attain the 100% value. So we will calculate our code coverage. We will elaborate it. And we will go to the comprehensive code coverage. We need to enable all these blocks. It will check in the block level as well as in expression level. If there is any FSM code also there, you can check this option. So after that you can simulate this. So as you can see, it is a 8-bit counter, so the output should go from 0 to FFF and from FF to 00. Then only all the input combination will be covered. But here I have covered from 00 to 0D. Many of the states have been left, so the code coverage will not come 100%. So we will check the code coverage. The tool used for calculating the code coverage is incisive comprehensive coverage reporting. So this is a command to invoke the tool. So you can see your 60% of the code has been exercised by your test bench, and also you can find out how many lines are uncovered by your test bench. See, the false part of this if reset has not been covered, so you can edit your test bench in such a way that it should cover all the possible case in your test code. So your test coverage mainly depend how you write your test bench. Okay, now after this simulation, this is all about the simulation. We are going to synthesize that RTL code into the gate level modeling. So for that, what we have to do, there is some standard cell libraries provided by the technology vendors. You can see this library. Suppose let me search some basic digital gates here. See, so this is a NAND gate having all the information, PVT information, process voltage and temperature information. These cells have been characterized in a virtuoso environment, and all the information about power, timing and delay have been written into a text file. So you can see the area consumed by the standard cell NAND gate, the leakage power, the pin-to-pin delay. All these information is stored in the .lib file. So what we will do, we will give this .lib file to the synthesizer. Okay, as well as my RTL code. So depending on this library, my synthesizer will convert that behavior modeling into gate level modeling. Okay. So the tool name is RTL compiler for the synthesis. It is a completely script based tool. We need to give a tickle script. So there is a provision in the tickle script. You can write all the commands in the same file and you can run that script. So it will execute command line by line instead of running one by one. So I have make a script for this RTL compiler. So I am invoking my RTL compiler as well as giving the script file name. So basically you should know what your synthesizer is doing actually. It is taking your RTL file as well as .lib file as an input. Okay, and it is generating a gate level netlist and your power, area and timing information. Okay, these all commands I have written into the script. If you will open this script, in the first line I'm setting the attribute for the library. Okay, in the second line I'm setting the attribute for my RTL code. The tool should know where my RTL code is located. Okay, in the third line this synthesizer is reading your standard cell library. In the fourth line it is reading your RTL code, and this step synthesizer underscore to mount, it is performing an actual synthesis step. And this last line, it is generating the repository file. First one is generating timing file, the power and area. So tool automatically itself generated all the power timing information. So this is the netlist that tool has generated from RTL to gate level. Okay, you can open these repository file also. See, 32 standard cells have been used from the standard cell library to implement that up down counter that has been designed by the your RTL compiler tool by some algorithms that have been written in a script. And this is a power information. So the leakage power consumed by your design is 1564 something, and total power is 28,000. The unit is nanowatt. If you will see the timing information, timing slack. So you should know what is a slack in the when you are dealing with the digital circuit. You should know what is slack. Slack means actually, slack is something that you can delay your clock up to that amount of time so that your circuit is going to operate. It is actually the difference between actual arrival of the data and required arrival of the data. It should not be negative in any case, because if it will be negative, your actual arrival of the data is late than the required arrival of the data, so it will not get latched properly at the positive edge. Okay, so you have to make sure that your slack is always positive. It should give a positive value, and using this slack you can find out the maximum operating frequency of your circuit. Okay,
ये क्या मिला है? वो लैपटॉप में चल जा रहा अब दबा ऑन करो बस हाँ बस
So this was all about the synthesizing. Now coming to the physical design, we need to implement this gate level net list in a silicon area, silicon chip. We need to implement that, right? From the beginning we are working in a front end work. Now we have to move to the back end VLSI design. We need to implement that circuit. So again, we have a different tool for working with the backend VLSI design, and the tool name is Encounter.
मास्टर इसमें चलाना है कंप्यूटर से कनेक्ट करना मैं बताऊँ तुमको हाल प्रोग्राम में डायरेक्ट हो जाएगा कोई दिक्कत ना हो तो एसेसरीज में इसमें इसमें इसमें
So this Encounter is a RTL to GDSII tool. It will the output of this tool will be your GDS file. So what we are going to do, we will input my area file, my power file, and my standard design constraint file to the Encounter, and depending on that it will generate my floor plan. So I'm loading this counter global. If you open this counter global file, it is having all the information, where the netlist is situated, what are the LEF file. LEF file stand for library extend format. It is having all the information about micros your standard cell library is going to use. So you can see how many standard cells have been used to implement that circuit. Right now we are ready with our floor plan. My floor is ready where my standard cell are going to be placed. Okay, now what I will do, I have to run the power rails to give the power to each and every transistor. Okay, actually what we are doing, I have decided the active area for the chip, where my standard cell are going to be placed. So I need to run these power rails from top to bottom and left to right, like this. Okay, so suppose I have placed my standard cell here, inverter. So instead of getting the power supply from here to the VDD, what can I do? I will run the strips horizontally as well as vertically, so that instead of getting the supply from instead of wasting the wire this much, I can get VDD just above my transistor and ground just below my transistor. So I need to specify the floor. Here I can mention the W and H ratio of my standard cell of the chip. So it should be 0.9. It is preferable. and these core to left and core to right is the distance you want to place your rails. Okay, so I'm taking this as a 2.5. These all values are calculated, these are verified one. So now your space is created for placing the power rails. Your floor planning is done. Next step is power planning. I need to place the ground and VDD rails. So I need to add the rings, VSS and VDD, and I need to use these metals. Suppose from top to bottom I'm using metal 8, and from right to left I'm using metal 9, and width I can specify 0.7 and place it like this. So VSS and VDD rails are placed here. So I need to connect this horizontally as well as vertically. So what I can do, I can add the strips here, and the strips I can mention if I want the number of strips or at what distance I want the strips. So all two options are there. So let's take 3 number of strips I want in my design, because it's a simple design counter, not a complex one. Like this. Okay, now I need to connect these rails horizontally also. So you can go to routing, spatial route, add this. So horizontally as well as vertically you have connected all the rails. Now next step, you need to place the standard cells here. Okay, placement you need to do. You can go to place standard cell. Okay, so you need to see the background window of the tool, what is going on in the background. See the total number of metal one length has been used by this tool is this much micrometer. Okay, it will be calculated by the tool itself. So these are the standard cells that have been placed here. If you want to see the any property of the standard cells, you can see this is the D flip-flop, and if you want to see the internal structure, you can check the cell option here. So it will give you the information how the internally layers are connected inside the cells. Okay, so after the placement, the next step was CTS. CTS stands for clock tree synthesis. I need to run the clock to the entire network. Okay, so what I will do, I will take all the clock buffer available in my design, and I will add it to my design. So you can see this clock network running into your design. Okay, So after the clock network, I need to check my timing details, whether any setup and hold violation is there or not in my design. So I need to debug the timing. So I can go to report timing, host CTS, setup analysis. So it will give you the information about slacks, worst negative slack and total negative slacks. Okay, it should be positive in any case, right? If it comes negative, you need to optimize your design. So what a tool will do during optimization, it will add some buffers and filters inside the design, so that if any of the path is violating by the setup analysis, it will insert some delay element. Okay. So after this CTS, I need to perform the routing step. I need to actually connect the standard cells. Actually, these have been placed. Actually, it is not connected. Only placement is done. So for the routing, I can go to S route. Okay. Just wait. Uh, Here I am specifying this point 0.9. Power planning, I'm doing this. Which I will take 0.7, and again I will do adding the steps. Placement, clock tree synthesis. Okay, so after this CTS, after I have to nano route. So after my physical design is ready, I need to do the power analysis also. Okay, so to perform the power analysis step, you can go to power analysis setup. So here two type of analysis you can do, static power analysis or dynamic power analysis. Also the switching activity you can specify, because it's up to you how much you want to make use of your design. Suppose you want to connect the IC in that environment where your input are switching at a much faster rate. Okay, so accordingly you can specify the switching activity. So you can run this power rail, and input activity, suppose in this case I'm mentioning as 0.02. So it will generate a repository file which will contain the information about power consumption by your each standard cells. Okay, so this is the name of the standard cells: mux, buffer, D flip flop, OR gate, and this is the column for internal power, switching power, and total power. So after this power analysis, I need to extract the parasitic components from the design, because this design is having metal and polysilicon layers. Okay, so some parasitics are definitely going to be there, because each material has some specific resistivity value per unit length. So larger the length you will use in your design, larger the resistance are going to be added. So I need to extract those components. So you can extract the RC value here in this files. So if you will open your file, SPF file, so it will be having the information about all the parasitic components that are being added due to the wires. Okay, so after that you can generate your SDF file. So that SDF file stands for standard delay format. Okay, so it will extract the delay from the standard cells and will put back into the test bench. Then we will perform the timing simulation. You can open that SDF file here. This one. So it is having all the path delay information for standard cell NAND gate. Instance name is G547. Delay are there. Pin to pin delay. This is a 3 input NAND gate. Okay, so from C to Y, this delay is there. This is the minimum matrix and this is the maximum matrix delay. It gives all the corner delay information, slow and fast both. So I will back annotate this file into your test bench. Okay, and again we'll perform the simulation, and I will check after how much time from the positive edge your counter is incremented or decremented. So suppose initially I was simulating my this netlist. This was my RTL netlist, right? And this one is my gate level netlist. Now I need to simulate this netlist, and I have to make sure the netlist generated by the synthesis tool exactly functions like my RTL code or not. Can I compile this netlist? No, because the tool doesn't know the behavior of these modules, right? tool doesn't know the behavior of D flip-flop. So I need to compile that file where all the module functionalities has been defined. So that has been defined in the standard cell library. So you can copy that standard cell library, this one. Here itself. Okay. And you can copy this timing information. So what does this line means? This is a, suppose whatever you will give in your test bench, the unit you should specify at the top. So it will take 140 nanosecond, and by 1 picosecond stand for time precision. Up to this much time you can find the delay, 1 picosecond. So from the simulation folder itself, I will launch my tool. Okay, now this time I'm going to compile my gate level netlist. Okay, this one. What actually I'm doing, initially I have compiled my RTL code that was having just a behavioral description. Now after the synthesizer have created my gate level netlist, now I am verifying it whether that netlist will behave as a up down counter or not. So I can compile my test bench like this. Now if you will zoom this, you can see the delay. Your counter is not incremented exactly at a positive edge, right? After some delay it is incremented. So this delay is generated due to those resistance and capacitance that has been extracted in that file, SPF file, from the physical design. Okay, so this is actual simulation result. When your chip is going to fabricate, your chip is going to behave like this. Okay, because it is ideal, you cannot design a chip without any delay, because delay are going to be always be there, parasitics, you cannot avoid those. But the things that is in your hand, you can minimize those to reduce the metal layers and polysilicon layers in your device. So why we need to do this post layout simulation? Because suppose in the at the initial point your specification was the delay should be less than 200 picosecond. Okay, initially your specification was like that, but after the post layout simulation your delay is coming out to be 336 nano picosecond. So will you going to fabricate this circuit? Will you going to generate the GDS file from this? No, you have to work on the layout part, right? You have to optimize your design, you have to optimize the area as well as a timing. Okay, so for that we have a standard multi-threshold standard cell libraries. What those library will do, they are having the standard cells with lower threshold value as well as higher threshold value. Those transistors which are switching at a faster rate, okay, they will be selected for a lower threshold value, because the power dissipation occurs in switching depend on the threshold value. If your transistor having higher threshold value, it will have a less leakage power, right? The transistor having low threshold value, threshold voltage, it will having high leakage subthreshold current. Okay, so those transistors which are sitting idle in your design, which are not switching at a that much faster rate, the tool will itself take a higher threshold value for those. Okay, so these are the optimization technique. So after this, mm, I can generate a GDS file from here, save as a GDS file. I can name that file as a counter dot GDS. Okay, so in the same folder, physical design, it will get generated. This one. Okay, so this is a foundry readable file, contain all the information about mask layers. Okay, actually the layout is a multi-layered step. It is not like in a single layer you have designed the layout of the chip. Layer by layer you need to connect. As this design was very simpler, so only two metal layers we have used, metal 1 and metal 2. Suppose you are designing a processor. Okay, so in that case you can you have to use at least 10 or 9, up to 9 or 10 layers. So the layout is a layer by layer process. Okay, you are familiar with the fabrication process, right? How the fabrication occurs, right? So okay. Hmm. So I will show you this LEF file. This LEF file will contain the information about the micros you are using in your design. What are the metal layers? So we are having a separate LEF file for 180 nanometer, for 90 nanometer, and for 45. Okay, so these are provided by the vendors like MOSIS or TSMC. Okay, so lastly, if you want to save this design, if you want to import this design in Virtuoso environment, Virtuoso is a again a tool for the cadence where we design analog layouts in the transistor level. Suppose you want to import this design in a Virtuoso, you can convert this file in a DEF. DEF stands for Design Exchange Format File. Okay, so that DEF file can be exported from the Virtuoso environment. And you can optimize this netlist also, or you can generate a netlist from the physical design. This is your physical design, how the gates are connected. You can generate a netlist with the name of counter.v. Okay, the same file you can open from here, counter.v, this one. So this will be having all the information, how many wires have been used in your physical design, how the gates are connected. Okay, every information. So if your design actually, what is a good design and what is a bad design? If a design is meeting your requirement, your specification, that is a good design. If a design is not meeting your specification, that's a bad design. You need to work out on the layout part. So if your design is meeting a requirement, you can generate a GDS file and can give to the fabrication industry. So lastly, we have generated the GDS file here. So this file you can give to the fabrication industry. Okay, so you have started from the RTL code. Okay, just you have written down your RTL code at a always statement positive edge, your counter should be incremented. Okay, and the tool has generated a GDS file which will implement that code on the chip silicon area. Okay, so this was all about the ASIC flow up to RTL to GDS. Okay, so I think we can end up our session here. If anybody is having any doubt, they can go ahead regarding this flow.
Good morning, sir.
Good morning.
Sir, myself Vimal Kumar Mishra from Madan Mohan Malviya University of Technology.
Okay.
Sir, I am working on MOS device and I have modeled my device on TCAD device simulator. Can I export my device to Cadence to use as a backend?
Backend. So you have modeled your device using TCAD tool, huh?
Yes, sir.
Actually, TCAD is a modeling tool, right? So you need to export the corresponding model files also. Hello.
Yes, sir. Yes, sir.
So you have modeled your transistor level diagram or a gate level diagram?
Transistor level diagram, sir.
Transistor level diagram, you have modeled it. So
yes, sir.
what
Can I export my device in Cadence?
So what is the extension of your file?
Sir, I have got it a IV curve and CV curve.
Okay.
From these curves, can I export my device in the Cadence tool?
No, you
what as a circuit level and after that backend as a different.
What is the format means? What is the extension of your file?
Yeah. You want to export it, that extension file.
The simulator, I have a .dat file.
Dat file.
Yes, sir.
Dat file you cannot export it in the simulator. Actually, this is not a modeling tool. If you will see, this Cadence is not a modeling tool. It will give you the complete flow from schematic to GDS. But if you have modeled your some device in the modeling level, you need to generate model file also. Model file will contain all the information about your doping density you are using, your oxide thickness you are using to model your device. So that extension of the file is .scs. You need to generate that corresponding file also.
I am from ABS Engineering College. You said that we can do RC extraction, parasitic RC extraction. So we could not do for inductance, parasitic inductance.
Inductance also you can export it, but for that you need to have a research license for this tool. You can export inductance also.
In research bundle we can do.
Yeah, but that is not that much important because we are generally focused for the calculation of the delay, and the delay is generally caused by resistance and capacitance only.
No, if we are calculating for current spikes, then it is required to calculate inductance also.
Yeah. If you are working some oscillator circuit, so definitely you need to extract the inductance also.
Okay, thank
from
you.
the layout. Thank you.
Any other query?
Hello, sir. This is Jyoti from ABS Engineering College.
From
Hello.
ABS. Okay. Yeah,
Yes, sir.
please go ahead.
Basically, I want to ask that can we interconnect MATLAB with the Cadence Virtuoso tool?
Sorry, ma'am.
Interfacing of MATLAB.
MATLAB with the Cadence Virtuoso tool.
Interfacing. What kind of interfacing, ma'am? I mean,
Basically, like as I have designed an algorithm in MATLAB, and I want to use their output in MOS. Like as if we take example of MOS, I want to put a width and length. I've calculated from MATLAB algorithm, and I want to put that value in MOS design. Like as I've taken oscillator.
okay.
Using MOS.
Actually, ma'am, the simulation file, you can export it into the MATLAB. It will generate a .csv file in the form of samples value. That file you can plot it in the MATLAB.
Okay, so that can be done on your Linux platform.
Linux only, yeah, exactly.
Not on Windows.
Yeah.
Okay, thank you.
Okay, GSS Noida, you have any query? Yes, please go ahead. Repeat your question, please.
Not meeting the requirements. So you need. Okay, I got your question. You need to optimize your design, and you need to optimize the layout as well. You need to reduce the metal layers you are using in your design. So these optimization technique you need to follow. Actually, the steps I have shown here, those all were the automatic by the tools itself. But suppose if you are working in custom IC design, that is analog design, there you have a option. You can reduce your layout as much as possible, because there you have to work in the layout manually. You need to draw the polysilicon layer, metal layers manually in the tool itself.
Another question.
Yes, ma'am. Please.
What should we do if there is a clock domain crossing? What case should be taken?
Clock domain processing.
Crossing.
Clock domain crossing, huh?
The question is not clear.
Yeah, I not get a question.
Where you are getting this kind of problem? Actually, your question is not clear. In which circuit you are getting this problem?
Suppose if it is a synchronous circuit,
Mm-hmm.
we are crossing it from one domain to another domain. If you are, suppose if the output of one flip-flop is given to the other domain,
Okay.
so by that, what case should be taken?
The same I have told you here, na? CTS. You need to synthesize this clock tree synthesis in the tool itself. It will automatically take care about all those steps. It will add all the buffers and filters, and it will take care that the clock is reaching at each and every block at the same time.
Any other query from any other center?
Sir, I continue my question from Vadama Margaret University of Technology.
Okay,
Yeah.
please.
Sir, I read an article from Pennsylvania University in which that they write a Verilog A model from the extraction of the data from IV curve and CV curve, and using these Verilog A model, use tool, cadence tool, and from that they made a ring oscillator.
Okay.
So my question is that how we write a Verilog A model from the IV curve and CV curve of the any MOS device?
See, suppose you are having the waveforms. Okay. From the waveforms, you can generate a Verilog A file. That is a executable file. Okay, that will plot a sample. I mean, they will be written down in some sample values.
Okay, sir.
So later on, you can import it in some other tools. That files. Any further queries?
Hello.
Yeah, please, ma'am. Yeah, ma'am. Tell me.
Sir, I want to ask you, if this tool gives us information information where to place buffers in clock lines to avoid the clock skew.
Where to place?
Where to place the buffer? Is this tool able to tell us where to place the buffer?
Yeah, definitely they will. After placing all those buffers, you can highlight those areas.
So, how do we know where to place the buffer if we want to avoid the clock skew?
No, it will not give you the option where you want to place. It will automatically check where it is required and it will place automatically. And if you want to see where actually they has been placed, it will shown by highlighting the areas.
Okay.
Actually, this is a yeah, ma'am.
Yeah.
Yes, next question.
How you have decided to choose width of the power line equal to 7? You have chosen in this one example power width of the power line 7 equal to 7. So how you have chosen?
Metal layer 7 you are talking about, right?
Yeah.
See, metal layers you can use 1 and 2, anything you can use, but each metal layers having some specific resistance and capacitance values. Like metal 1 you are using copper, metal 2 are using some other materials. So our main aim is to reduce the resistance in the device. So it is not mandatory to use metal 9 and 8 only, but I have worked in this design by using metal 1 and 2. So in that case I was getting some more delay. So that's why I suggest you to use metal 9 and 8 in this design.
Means prior we have to find out the delay. After that we have to decide.
Yeah, exactly.
Okay, thank you. Any other question from any other center?
From the JSS Noida, one more question.
Yes, ma'am.
Does this tool use any algorithm for going for the placement or?
Yeah, every algorithm is written in the script. In the background window, only the script is running. Okay, it is using many algorithms. The many iteration steps is used to follow for optimize the entire design.
और इंडक्टर का लेआउट कैसे डिजाइन करें?
Not audible, ma'am.
Hello, sir. Good morning.
Just wait,
Sir,
wait.
can you suggest any how we can design a inductor layout? I'm
Inductor
from
layout.
GPIT. Yes.
Inductor layout you can design. There will be option when you are working in a cadence tool.
Yes.
Yes, sir.
Yeah, so from the GPDK 180 or 90 there will be option for invoking the inverter layout.
Okay, sir. Okay.
Okay, JSS,
Okay, thank you.
you can complete your question.
So I was asking that the user have the option. Does the user have the option to select the algorithm by going for the placement or routing?
User, no, user don't have the option.
So there is no option
It
of
is a script based tool. Every script has been written, so you cannot change that script. If you will change the script, your algorithm will change, and you may not get a optimized design, because those scripts were written by a very experienced designer.
Okay, next question please.
Optimize the design by choosing the algorithm. We can only optimize by placing the buffers or like that.
Actually, if you are going for fully custom design, you can placement is in your hand only, right? You can place your components as per your requirement, but if you are going for semi custom of design, then it is automatic, right? Otherwise, you can place your components. If you are going for fully custom design, you can place your components at your end.
Suppose you are designing a NAND gate using PMOS and NMOS. Okay, so the layout of that NAND gate is completely in your hand. How you place the transistor, how you manually connect those transistors using metal layers, so that is in your hand. But when you are moving some higher design, processor, ALU you want to design, so in that case you need the automatic steps only. You cannot connect thousands of transistor layout by manually.
So, any other question from any other center? So I think if there are no more queries, then we can proceed with our tea break session. So in this session, you have learned about the complete design flow of Cadence. Actually, Cadence is very popularly used tool at present in research area. If you are doing your PG or doctoral research, then really this tool is extensively used in different academic institutes, as well as it is also industry standard tool. So many industries, they are using this tool at present. So this is the complete flow of Cadence design. So I think it was useful for all of you, and whatever doubts you had, those doubts were cleared. So with this, I would like to thank Engineer Varun from NTUPER Technologies, who are distributors for this Cadence design software. We are really thankful to you for accepting our invitation and giving us this complete exposure of this Cadence design flow. So with this, we end our session at this point, and we will proceed with our tea. And at 11:30, we will be right back with our next session. Thank you.
एनर्जी सेव करने के लिए कह रहे हैं।
ये तो नो ब्रांच here or kindly change your views regarding it. इसी में नाम थोड़ी डाल
ये तो कह रहा हूँ मैडम को ये तो
इसी में नाम डाल दो। और टीचर दिन भर एक कोई आता है मोबाइल मोबाइल नहीं है सर मोबाइल नहीं है
बैटरी बोला जीवन से करते हैं क्या
मैं कहना डीएम वेरी ना मैं उनको खड़ा करके पहले पूछना लास्ट लेक्चर में ये हुआ था आपको ये पता नहीं क्या क्योंकि जब तक ये पता नहीं होगा तब तक ये आज का नहीं समझ में आएगा
गो गेट आउट फ्रॉम द क्लास
जब मेरे क्लास में आएगा मेरे क्लास में आएगा उसका सेमेस्टर लगेगा तो पूरे साल का रहता है
ऑड में जो होना था
सर मैंने आपको बोला था ना आपको सर आपको जो बोला है ना हमने वो करिए सर
तो भागो
हाँ ये बहुत बड़ी स्टीम इज द वन ऑफ द बेस्ट सॉल्यूशन फॉर द सॉल्यूशन कोई बीमार पड़ेंगे इसमें अगला के दूसरे को बीमार पड़ेंगे
आइए वेलकम सर
इस फीडबैक होगा बहुत टू चाय चाय होगी चाय
और सर
अब जब हम स्टेज कमेटी में हाँ एक बोले तो मुझे डे वाई मारा मुझे सर है और नाम है ज्योति का नाम है और कुछ परफॉर्मेंस है कि नहीं है स्टूडेंट के सर हाँ है आप टीचर्स देख तो टीचर्स होती है वो कुछ याद नहीं कल्चर का नहीं है यार कल्चर में
So we are going to start our second session of the day, and it will be taken by Professor Rajivan Chandel ma'am. She is working as a professor in Department of Electronics and Communication Engineering in NIT Hamirpur, HP. She has received her BE degree in Electronics and Communication Engineering from Thapar Institute of Engineering and Technology, now it's Thapar University, Patiala, in 1990. She did her MTech in Integrated Electronics and Circuits from Indian Institute of Technology, Delhi, India in 1997. She was awarded PhD degree from IIT Roorkee, India in 2005 under QIP scheme of MHRD, Government of India. Her research interest is in electronic circuit modeling and simulation and low power VLSI design. She is a fellow of IETE, life member of ISTE and ISSS and member IEEE. So I invite Professor Rajivan Chandel ma'am to proceed the session, please.
Thank you. Thank you so much, and very good morning to all of you. First of all, let me thank Dr. Rajesh Mehra for having invited me to this particular short-term course. I was little wondering in the beginning about the name of this program, that what is ICT-based short-term course on VLSI design, but I'm really happy to know that many other institutes, around 24 he has told me, are also associated with this program, and they're also viewers and participants of this program. So it's really I'm very fortunate to be associated with so many institutes, so many faculty in one go. And I also requested him to invite the students also, so that we have some local participation also for this program. Sir, I take your permission to begin. So today we will be talking about high performance CMOS design. It's from a VLSI designer's point of view, VLSI designer's perspective. In fact, many sessions must have already been conducted in VLSI design, but still I do feel that we need to take up things slowly and build up from basics and then go to the more advanced things. So in the first session, I'll be covering up about CMOS design, particularly digital CMOS design. And in my second session, I would be taking up advanced design issues in interconnect designs. So as we all know, the first integrated circuit was given by the great researcher Jack Kilby at Texas Instruments, and slowly and steadily the progress in integrated circuits has been enormous. And in 2003 itself, Intel Pentium 4 microprocessors were there, which were having 55 million transistors. Likewise, your DRAMs or the memories were also having capability of 250 megabit, which is more than 0.5 billion transistors. Now this is around 53% compound annual growth rate, which has been seen over 45 years. And now from 2003 to 2015, another enormous change has been witnessed in form of quad 2, quad 4, quad 8 type of core processors, which are having much enhanced number of transistors in billions and trillions. So large or very large scale for that matter, these integrated circuits are driven by miniaturization of the basic devices, that is the transistors, which form the heart or soul of any integrated circuit, particularly in VLSI design. And of course, smaller is cheaper, faster, lower in power. We will see how that is all about. And the very aim of all this, very aim of VLSI design, electronic industry, or for that matter ICT, is that human life should become more comfortable. That is the basic purpose of all this. Let us go ahead and see. This is starting integration of the circuits. So levels have enhanced from single to 2 transistors, and then small scale integration, medium, large, very large scale integration. And very large scale integration, you would say something 10 raised to power 6. When it is million, 10 raised power 6, we call it VLSI. Anything more than that ranges in ULSI range, or that is ultra large scale integration, or giga scale integration, or wafer scale integration. But the word VLSI is so sweet and has been coined since 70s. So we now also use the same word VLSI, but we have to keep in mind that if we are talking about the latest devices or integrated circuits, we are actually talking about ULSI and the higher integration levels. But we still in general call them all as VLSI circuits. So you can see this graph, which is taken from Intel, and it shows you very clearly, this nonlinear graph shows us the enhancement in number of transistors per chip, or chip complexity, and it has enhanced over the years. And the great researcher Gordon Moore, who gave the law in 1965, when we were not even born. So he had such a great vision and a view that this technology is bound to see many more enormous sophistications and enhancements in years to come, and has well stood the fact, and it has been true over the years. And this thing, the law which he made, that the number of transistors on a chip would double every 18 to 24 years, and he made a prediction that semiconductor technology will double its effectiveness every 18 months, has stood by time. And still, you know, when we have such huge level of integration on certain say 1 inch by 1 inch wafer, still there will be some limitations. Now the limitations which have been reached are in terms of the size of the chip, maximum chip which we can have, and of course the semiconductor itself. So the limitation will be the interatomic distances actually. We cannot go below that. So that would become the limitation, and already we have reached nanometer regimes, whereas we started with micron and micrometer dimensions, then sub-micrometer dimensions. So you can see already in 1995, so you can see this point, already in 1995 it was sub-micron, that is 0.5, and below that you can see the trend has been an exponential decrease, and now we all work in nano regimes, and the technology presently talks about 32 nanometers, 22 nanometers and below. IBM claims that transistor, MOS transistor with 6 nanometer channel length has been given by them. So let's come to the topic with this brief introduction, and we would talk about a VLSI circuit has a huge number of transistors. Silicon and silicon or a semiconductor chip, it houses the integrated circuits, and the main beautiful part is that the components or the MOS devices and the interconnections which connect these MOS transistors on an integrated circuit are integral part or inseparable part of the integrated circuit, and that is why the word integrated is used in integrated circuits, not merely due to the integration level. Then due to VLSI systems, you can see, you all see day to day that how our desktops have reduced in size, how the laptops have become more handy, and how your mobile systems, they have become very, very sleek with huge number of functionalities added to them. Despite the fact that they have become smaller and huge functionalities there, they have become smaller. It is all because of this, the dimensions reduction in the number of this transistor, which leads to enhancement of chip complexity, which gives us the flexibility of adding more number of transistors and thereby more number of functionality into it. So large potential exists for IC design and fabrication for high performance computing, because that is what is the aim of the course or aim of the technology, that more higher the complexity, the better should be facilities provided to the customer who will be actually using those facilities. So integrated circuits as such are multi-terminal devices that provide an array of functions and applications. This is a typical board on which you see a number of chips which are shown here, and all this huge board comprises of a number of integrated circuits. We shall be talking about what is happening inside. Before that, let us keep in mind that VLSI design and technology or fabrication, they go hand in hand. That means whatever is the sophistication in designing, that can be well done or well understood if we have a proper understanding of how the technology is improving or enhancing simultaneously. What are the improvements being done in it? Major VLSI designers are your Texas Instrument, Synopsys, Xilinx, Cadence, Mentor-Graphics, and the list goes on. And some of the houses which are actually associated with the fabrication as well in India are SCL, Mohali, Siri Pilani, DRDO, and some fabrication labs in IITs. Of course, the other major houses or designers, VLSI designers on the left hand side, they all have the facilities for fabrication technology abroad. We have various VLSI tools and softwares. So SPICE, then tools related to Cadence, Mentor-Graphics, Eldo of Mentor-Graphics, then Synopsys, Tenor, ORCAD, and Xilinx provide different EDA tools wherein we can either go in for schematic entry, or we can use the hardware description languages, your VHDL and Verilog. Then some boards in the form given by Spartan and Vertex, they can also be used, wherein we do not need to go in for fabrication of the design which we make. We can directly burn the code in the FPGA type of kits or CPLD type of kits and configure that particular hardware into our hardware using hardware description languages. So different ways are there, ways and means of learning how to implement what we are actually designing. Let us come to the basic CMOS technology, which is used and for designing and fabrication. And when we see the cross-sectional view of a CMOS structure, it is well understood that we can be making NMOS transistors on P substrate, and CMOS means complementary MOS technology. So we will require N-well for the formation of the PMOS. So this is how the NMOS and PMOS would look like on in a fabricated chip, with other with the terminals showing the source and the drain, or the and similarly for these two, and the center part shows you the presence of oxide by this very thin layer on top of which you have. Earlier it started with metal, that is MOS structure, metal oxide and semiconductor, but with passage metal has been replaced by polysilicon due to a couple of reasons which we shall take up later on. So this is how you make a CMOS structure. So we have to keep in mind that what will be the densities of the material, doping densities of the substrate or the well which is behaving as the substrate for the PMOS, what will be the material of gate, what will be the dimension of oxide thickness, and all these things. So on one side, when we are using a particular technology, your technology will limit those particular dimensions. On the other side, when you are designing some circuit using a particular technology, you can give any design, but have to keep in mind that what will be the dimensions, what will be the technology actually looking into. So both the things have to go simultaneously. If we have a fair knowledge of the technology, then when we are designing a particular circuit or a particular system, we know what will be the major limitations or non-ideal effects which will be associated by downsizing the technology or by scaling of the technology, as we are going from sub-micron to deep sub-micron to nanotechnologies. So everything is not rosy. There are many advantages as well as disadvantages associated with each with any good thing, and therefore knowledge of technology has to be has to go hand in hand with design. This is the three-dimensional view of the same structure, CMOS structure, and obviously it is something like a cuboid which we have shown here, and you can see for yourself that how the gate region has been shown. And in a CMOS structure, the gates of the NMOS and PMOS are connected. That is what is shown here. The drains of the PMOS and NMOS are connected. That is what is shown here. And the rest of the connections would go according to these when you have more number of such CMOS structures to design a complete system. So as such, your MOS technology is preferred in ICs, integrated circuits, over BJT or bipolar junction transistor technology because of the flexibility in scaling or feasibility in scaling, and that is limited in BJTs because of its very structure, because of its vertical structure, where you have to see the limitation of two junctions coming into picture, whereas that particular limitation is not associated with MOS structures, where it sees horizontally, the limitation is seen horizontally at the source and the drain end. That means for the channel length. Likewise, static power dissipation is low particularly in CMOS technology as compared to bipolar as well as NMOS technology, when half the transistors would be off for a particular pulse width, per pulse time. So that gives the advantage of power dissipation saving. Then high input impedance is that is what was actually the basic necessity for going into MOS, so as to enhance the input impedance by the presence of oxide layer as compared to BJT, which has a direct coupling of the base region with the other parts. Here the controlling or the gate region is not coupled directly, and that enhances the input impedance. Then it has high noise margins, which are again very useful for particularly for any digital design. High packing density is possible due to the first reason. Then high delay sensitivity to load. So load has a direct impact on the delay of the system or the circuit. Usually we talk about capacitive loads in MOS circuits, because any circuit would be connected to another similar circuit which would be formed due to MOSFETs or something like that, and those would again be associated with different capacitances, and that is why effectively you talk about capacitive loads in these circuits. MOSFETs are bidirectional devices. That is again its beautiful aspect, because source and drain, they have identical dimensions and identical doping levels, unlike BJT where the emitter and the collector, they have different dimensions and different doping levels, and hence we can interchange the source and the drain in the MOS transistor, thereby giving it more flexibility for layout making and fabrication of the device on the silicon, unlike BJT where we have fixed emitter and the collector regions and we cannot interchange them, and hence it would require more area. As such also, if you compare same current carrying capability device BJT and MOS, it would be typically BJT would be typically 17 to 20 times bigger as compared to the MOS having same current carrying capability. So that gives you a huge difference in area at the first hand itself, and then when the terminals are not interchangeable, that again leads to further area usage. Then CMOS leads to low dynamic power dissipation, and that is typically because for any pulse time period, either P MOSFETs would be working or N MOSFETs would be working. So as such, when we see a CMOS device, it has one NMOS and one PMOS. Let us go to the system. Let us go to the to this circuit, which shows you the PMOS and an NMOS being taken as a driver. This is your enhancement NMOS, and this is your enhancement PMOS as driver, as load, and this is your driver. And this we have shown an ideal system, ideal input step and ideal step output, which is inverted, but it will be never so, because a MOSFET is associated with a number of capacitances and junction capacitances as well as oxide capacitances, which never charge or discharge instantaneously. So we can never get ideal outputs from any CMOS circuit. But as such, if you see, both the PMOS and the NMOS have a function to play as a driver and the load in a CMOS device. So these are the inputs which will be, if Vin is the input to this circuit, it will be directly equal to whatever is the gate to source voltage of the NMOS, and likewise Vout will be directly equal to whatever is the drain and source value of the voltage of the NMOS. And likewise, if you have to see the PMOS, then its input would be whatever is input minus whatever is the supply voltage, and so will be its output. So you have to compare these values when you have to consider their performance. So as such, if you see, if you give any input here, suppose we give 0, so 0 means your two transistors, they are dual of each other. For 0 or low values, this transistor will be on, and if this is on, your VDD is connected to output, you are getting high output, and if your input is high, you will be getting this NMOS transistor will be on, and that means your output is getting connected to ground. It will discharge, so output is low. So that is basically how an inverter works. Any inverter, we are talking about a CMOS inverter here. So if you check the input versus output characteristics, which is known as voltage transfer characteristics or VTC characteristics, this particular level is, say, up to the maximum value is your VDD, whatever is the supply voltage. So somewhere here midpoint would be the threshold of the inverter. Threshold means where the transition would take place from high to low or low to high, vice versa. So from 0 to this point, for input, it will be treated as logic 0 or low logic, and correspondingly the output would be high and or VDD. Likewise, from this midpoint to maximum value, input in positive logic is treated as 1 and the output corresponding to that is 0. So this is an ideal VTC which we do not get in a practical circuit. It would look something like this, where you have exponential decays of the signal. Likewise, here also you have those particular points. So the point VTC is a very important characteristic in determining many parameters and properties of the devices and the circuits later on. So in this you have important voltages. So one is the VIL, where the gain. So whenever we have VTC, anything related to output and input, so the most important parameter which can be determined from this graph is voltage gain, that is small change in output by small change in input. And at a particular point here you can see the gain would be equal to -1, since it is traversing from left to right, or it is an inverter. From that point of view also you can see that the gain would be always negative. So the two important points where there is a changeover, they are termed as, where the gain is -1 at the 2 points, those are termed as VIL and VIH, where VIL is the maximum input voltage which will be treated as logic 0, and VIH is the minimum input voltage which will be treated as logic 1. So that gives you the minimum point. So from here to maximum value, that is logic 1, and from here to 0 to this point is logic 0. So this, if you see the change in output with respect to change in input in this particular region, what do you see? What would be the gain typically like? It would be less than 1. If you see the same change here in the last region, which is beyond A is equal to -1, here too the similar effect is there. V out by V in is very less, so gain is less than 1. And these two are the points where gain is 1. And in the middle region, you will see transition from in the output is very large. That means delta V out is very large as compared to the change in V in. So that means the gain is very large in this particular region. So this particular region between A is equal to -1 is usually used for analog circuit designing, as gain is high in this region, and the two extremes where your transistors are working in maybe saturation for NMOS and cutoff for the PMOS or vice versa, they will be used for digital circuit designing, where gain is not important but functionality is important. So this this gives you the three values of the of the voltages of the VTC curve, and when you want to attain a VTC, we would like it should be as close to the ideal characteristics as possible, and for that you need to have symmetry in the circuit, and therefore VTC should be midpoint. And if that is true, then to an extent the best VTC is obtained. And if you see, when V in is at the midpoint of the curve, so that means at this point both V in, that is VTH, and V out, both are VDD by 2, and at this point both the transistors are in saturation, and at the extreme ends you will have either the NMOS off before it is the threshold voltage of the NMOS, or it enters directly into saturation, because output is very high, input is very less, and that directly gives you that NMOS would be definitely going into saturation region, and PMOS definitely going into linear region at this particular in this particular point, because VDS of PMOS would be whatever is output minus VDD, and that difference becomes very narrow. So that takes PMOS to linear region of operation. So when you see the midpoint, both the transistors are in saturation region. And if you see any this device, even if you connect a capacitive load here, or if you connect a MOSFET here as fan out, you will see that if you have connected a MOSFET here, that means you are connecting this output to gate. So gate will never, no current will flow in gate in the normal condition. Okay, so that means whatever is the current in the load, that current will flow in the driver, and that is why we take this configuration that your drain, whatever is the drain source current in NMOS would be equal to the drain source current in the PMOS. So we take these normal expressions for IDS in saturation region, and we consider one for PMOS and for NMOS, and from this we can substitute that if Vin is equal to the threshold voltage, which we have discussed in the previous slide, that would come in this form, and this gives you the relationship, as well as you can understand that how important is VTC in deciding the threshold voltage or the transition point of the of a CMOS circuit, where whatever is your main VDD supply voltage, whatever are the threshold voltages of NMOS and PMOS, whatever is the ratio of the transconductance parameters of the two transistors, that is NMOS transconductance and PMOS. You can even add Cox here, mu and Cox, because Cox is common for both. I have deleted that. So this particular parameter gives you a very intelligent conclusion that if these two currents have to be identical, something has to be there. So Kr has to be 1 if you want that this current should be equal and symmetry should be maintained in the circuit. And for that, if you substitute Kr as 1, and if you also take the two voltages equal, threshold voltage is equal and opposite, then you land up in this conclusion that because of the difference in the mobility of holes and electrons by a factor of at least 2.5 to 3 times, you are required to make the PMOS transistor 3 times or 2.5 to 3 times bigger as compared to the NMOS transistor, so as same current carrying capability is obtained in both the transistors. So this becomes an essential requirement. Other than this, when we have to see the performance of the circuit, we see 3 major parameters, that is the delay, which will be associated with the parasitic resistances, capacitances, inductances, and supply, whatever is the supply voltage. So then power dissipation, whatever is your dynamic power, resistive power, static power, all those will be the deciding factors, and correspondingly you can see on right hand side what are the limits. So your frequency of operation, different cooling arrangements may be required. If you have a very huge system in which CMOS transistors are being used or CMOS technology is being used, then obviously you will require certain special techniques so as to contain that power. And then likewise, with such huge chip complexity, crosstalk, temperature effect, process variation effect, which affects the formation of the different transistors, all have to be kept in mind. And for that, not only the devices but the interconnects do play a very important role. So as seen in the previous slide, if we talk about the CMOS propagation delay, let us say that this is your input with some small rise time and fall time, and correspondingly you will get an output. So the variation can be seen. The important variations are at the transition points, not at the static points or the fixed values. Okay, so whatever is the output corresponding to this input would actually decrease exponentially before taking the final logic 0 value or logic 1 value. So both these points or the transition points are important, and for deciding the propagation delay of the device, both these regions are considered, and the propagation delay corresponding to change in input from low to high and corresponding output from high to low is termed as tau PHL, and likewise the other end is termed as tau PLH. So let us see, you also see two more points being discussed here as VOL and VOH. These are the minimum and the maximum output values which can be obtained in any CMOS circuit. Usually for CMOS circuit, VOL is 0 and VOH is equal to the supply voltage VDD. But if you have a different technology, for example NMOS, then it is not fixed that VOL will be 0. That is why this lower and the higher values are considered to be taken in generalized formation of these characteristics. So this particular value from VOH to VOL is important if we have to find out the propagation delay, because V50% is what actually we are looking forward. So what is the difference between the or time delay which is seen when input is 50% and output becomes 50% at the two edges, and the average of these two values actually gives you the total propagation delay in the system. That is what is given, that how you define V50%, that is difference, half of the difference between the maximum and minimum plus the minimum value. So this relationship of tau PHL is associated with parameters where CL is the load capacitance of a CMOS circuit, then mu n Cox WIL is the transconductance parameter of the MOSFET, and VDD and threshold voltage. Since when input changes from 0 to 1, so that means when input is high, your NMOS transistor is actually operating. So whatever are the parameters of the NMOS transistors, those will be affecting this particular transition time. And when input changes from high to low, your PMOS transistor will be operational, and therefore tau PLH will be associated with PMOS transistor parameters. So that gives you this particular expression where your threshold voltage of the MOSFET, VDD, and its aspect ratio of width by length of the channel, or in general transconductance parameter, they will be important deciding factors along with the load capacitance for the delay. Likewise for tau PLH, all other parameters, the expression would be identical except that the threshold voltages would be for the PMOS transistor, and this mu p would be the mobility of holes. Likewise this W/L ratio would be that of PMOS transistors. So as such, if you see how to control delay, then from these expressions we can see that it has an inverse relationship with W/L. It has a direct relationship with CL. It has an inverse relationship with VDD minus VT. Okay, so larger the W/L ratio means larger the transistor, lesser will be the delay. Likewise, higher VDD would lead to lower delay, and lesser the threshold voltage, because it comes as VDD minus VT term. So lesser the threshold voltage, lesser will be the delay. Then threshold voltages, see the threshold voltages and VDD, they're actually technology oriented parameters. We have less control over how much VDD or threshold voltages we can scale down, and therefore W/L or the aspect ratio of the transistors becomes a very important design parameter in the hands of a designer for any circuit. Likewise, when we talk of power dissipation, we have three types of power dissipations in the circuit, and That is firstly the standby or the static power dissipation when we are not changing the inputs, okay, they're static. Then you have the switching power dissipation when there is a transition from low to high or high to low. And then finally there is short circuit power dissipation in the device when both the transistors are on. In the ideal case, when input is sharp 0 or input is sharp VDD or 1, in those cases it's okay, one transistor is off, the other is on. But we have seen in the VTC characteristics that logic 0 is not 0, but it's a complete range from 0 to VIL position. Logic 1 is from VIH to VOH position. So therefore it's a complete range, and therefore we need to consider that what will happen if your input is more than 0 in the logic 0 input. Okay, so if it is more than 0, say equal to VTN, that is threshold voltage of NMOS transistor, your NMOS transistor will become on, PMOS is already on. Okay, so that means from that point onwards, threshold voltage of NMOS onwards, both the transistors are on. Till you reach a point VDD minus VTP, both the transistors remain on in the entire VTC curve, except the two edges. Okay, so that means when both the transistors are on, there is one common current flowing through your VDD and ground lines, which is termed as rails, the current between the rails, and that is your termed as short circuit current, which leads to short circuit power dissipation. You will also acknowledge the fact that when we are not using our mobile systems, handsets, they do discharge, and that is due to sub-threshold current, and sub-threshold current flows even in static condition. That is what is being shown here, that PMOS is off, this is on, but it is at the same condition for a long time, still there will be sub-threshold current conduction in the device. It is parasitic but and unwanted, but now designers are using this particular current to form a complete sub-threshold logic, which is useful for devices or circuits which require very low currents, for example your biomedical applications. So one is sub-threshold current in the standby condition, and other is the formation of different PN junction diodes due to the very structure of a CMOS circuit or a CMOS structure. So wherever, for example, this is your N well, so wherever there is a change, so here is P plus, this will be N well. So there, that means a PN junction will exist here, it will exist here, it will exist between the well and the P substrate, so another PN junction diode here, likewise in these two portions. And if the PN junction has the same potential at both the ends, these two are the body contacts. Okay, this is P substrate and this is P plus, so this is simply for the body contact, and likewise because it's a 4-terminal device, a MOSFET is a 4-terminal device, so that is what we are showing here, that the body is connected to either VDD in case of PMOS, or it is connected to ground in case of NMOS. So if any of the diodes it is having same potential, that means if N is also at ground and due to this P is also at ground, it means it is unbiased. And if you consider a transistor here in PN junction parasitic, all these PN junction diodes are parasitic, we are not making them, but they come on their own because of the structure of the CMOS. So if this is at VDD, it is being connected here, this is also at VDD, it is also unbiased, but if this is connected here to VDD, minus negative terminal is connected to VDD, likewise in this your this is connecting the positive terminal to ground, so these diodes become reverse biased, and likewise this also become reverse biased. As a result of this, you have one I0 current, that is reverse saturation current in the reverse bias flowing in this diode, another is in this diode, so that overall becomes twice of I naught in this particular structure, and that is why the total static power dissipation is controlled by the reverse saturation current and the subthreshold current. Likewise, if we see the switching power dissipation, I'll come to this point that whenever you have the discharge, whenever you have the charging or the discharging, so this is the charging. Actually, if this transistor is on, it will be charging the load. If your this transistor is on, it will be discharging the current. So this is actually discharge current. So it will be discharging. So we find out what is the charging and the discharging conditions, and in these using this expression which we use for any capacitor, that capacitive current will be CL V out V dV ddt by of V. So that is used to find out what will be the energy and power associated with that particular configuration. So power is always rate of change of energy with respect to time, or you can consider this particular relationship, and using this particular relationship you can find out the charge energy, and charge stored is identical or equal to charge dissipated, energy dissipated in the capacitor, and therefore the energy dissipated will be half of it. So half CL VDD square. Likewise, in the discharge case, you can use a similar analysis and find out whatever is the energy which is during the discharge condition, and the sum of these two gives you the total energy which is dissipated, and you know power is energy by time. So for one time period, if you see it, it comes your switching power dissipation, and which can be given in terms of frequency, CL and VDD. So three parameters determine this power dissipation, but here it has a quadratic relationship with the power VDD supply voltage. So that becomes more important as a power dissipation. And we have already talked about this short circuit current when both the transistors are on. So when one transistor is off, that is the NMOS, at that time there will be no current in the in between the two rails, VDD and ground. So that is shown here. Then it continues to increase till both the transistors at the midpoint are at saturation. So that gives you the maximum value. Then again it starts decreasing because one goes into saturation and one is in linear. So it starts decreasing. And then when you enter the second switching point, VDD minus VTP of the PMOS, here again it goes off. So that means you will get two peaks of this type in any one time period. And we take the mean of this particular current or the average current associated with this, and that becomes your short circuit power, which is a function of transconductance parameter of the transistors, frequency, rise time or fall time, and VDD and threshold voltage. So again you can see, you have seen in the delay also similar type of parameters like your CL, your VDD, your threshold voltages, transconductance parameters were affecting VDD delay. Here also in power also similar parameters will be affecting it, but usually if you have seen it carefully, in both the cases the parameters usually have inverse relationship. For example, if you see this particular parameter CL, it has identical relationship with CL. Delay was also increasing, with CL power is also increasing, but VDD has a different role to play. VDD has it has a cubic variation in case of short circuit power, and VDD minus VT was having an inverse relationship for delay. If we were increasing VDD, we were getting lesser delay. Here if we are increasing VDD or taking a higher value of VDD, power dissipation increases. So lower VDD would be definitely better for lower power dissipation, but it would lead to higher delays. So that means trading and optimization is required to take the best value of the parameters. This is one example. Likewise, you can check for other parameters also, that how they should be traded to get an optimal VLSI design. Okay. So this is an example, and if you consider that I naught and I subthreshold currents are identical, if you take a value of K transconductance parameter, then transition time, frequency, VTN plus minus 1, and some value of CL. So this is one typical example. So if you find out the static power dissipation, it would be of the range 0.015 microwatt. If you check the switching power dissipation, it would be of the range 5 microwatt using this relationship. And likewise, if you see the short circuit power dissipation, it would be of the range 2.25, giving you a larger overall total power dissipation of 7.265 microwatts, which is showing that obviously switching power has a major junk portion of the power dissipation. But as you scale down the technologies from deep submicron to nanotechnologies, the short circuit power dissipation can become much higher, and that is point to be remembered when you deal with such circuits in nanotechnologies. So now any CMOS circuit could be given in this form, where you have a PMOS network as the load and NMOS network as the driver. For example, if you see the 2-input NAND gate or 2-input NOR gate, this is what a typical circuit would look like, where you have PMOSFETs are dual in every sense of NMOS. So if the two transistors, 2 NMOS are in series, they are bound to be in parallel in the other half, and likewise. So if I want to make any circuit now, any CMOS circuit, you can consider a similar configuration of N MOSFETs and P MOSFETs, and take dual of these in the PMOS logic. Now we have identified what would be the delay, how would the power dissipation of a CMOS inverter vary with different parameters. And here we are talking about a complete circuit, a different circuit. So that means if I can change this particular circuit into an equivalent CMOS circuit, it would give me a direct or first-hand approximation of what the circuit performance would be like. And for that, you have to keep in mind 3 important design considerations. One is the chip area. It should be minimum. Chip area utilized should be as low as possible. Propagation delay should be low, and power dissipation should also be minimum. So these are the 3 main design criterias which are to be kept in mind, and using these power dissipation these criterias, if you see any circuit, any CMOS circuit, you will find that either the transistors are arranged in series or they are arranged in parallel. So that is the beauty of CMOS circuits. For example, if you see this NOR gate, you will, if I want to convert this into an equivalent CMOS inverter, then I will have to change this particular parallel combination of 2 gates into an equivalent single gate. Likewise, if I see these 2 series connected transistors, I will have to change it into equivalent PMOS transistor. So if you see these two, any parallel combination of transistors, the main current which will be flowing through an equivalent transistors is actually equal to the summation of whatever is the parallel combination of the transistors. And if you just associate yourself with the transistor IDS current, it would be of the type whatever is transconductance, that is mu n Cox into W by L into VGS minus VT into VDS. So VDS is identical as they are in parallel. So VDS is identical if I give same input to all. So that makes VGS minus VT also identical. Mu and Cox is identical. So only parameter which is left is W by L of each transistor. So the equivalent W by L means it should be summation of all the transistors. So agar yahan pe if there are two transistors here, we get twice into whatever is W by L. This is dual of it. This was parallel combination, this is series. So you can check in terms of resistances of each transistor. So resistance of any transistors would be whatever is VDS across it divided by whatever is current across it. So using that particular relationship, you will get that the overall length of the transistor increases if they are in series, and the width of the transistors increases if they are in parallel. So that like that there can be n number of transistors in this series parallel combination as you have in this particular circuit. So you can slowly and steadily you can convert them into an equivalent transistor in the PMOS and the NMOS side and get an equivalent transistor like this. Once you have an equivalent transistor, then you know all the relationships, how the power is varying, how the delay is varying, and use those to find out what should be the dimensions W by L of individual of these equivalent transistor, and then of course you can find out the values of the individual transistors. Now how do we decide this? By taking those three criterias. I want minimum dimensions or minimum chip area, I want minimum power dissipation, I want minimum power delay. So using those constraints, design constraints, you can decide the values of your transistor dimensions. So that is what we have discussed so far, and now let us come to when we talk of high performance. So this was the basic fundamental, that how do you go about designing any circuit, particularly in digital, from a digital point of view. So if you want high performance circuits, this means it should have high speed, that means low power, low delay and low power. Whenever a circuit has low power dissipation and low delays or high speeds, that becomes a high performance. So we have seen in general that how the power and delay can be controlled by controlling the different parameters which are associated with the circuit. Furthermore, if you would like to see that how dynamic power is associated. So dynamic power I have not shown, but you have to take switching activity also into consideration in the relationship. So switching activity times whatever is the relationship which we have obtained, that becomes an important point, as it has a direct relationship with the power dissipation. So lower the switching activity, lower the CL would, and lower VDD would be beneficial for reducing or containing the power dissipation. Likewise, operating frequency, if you have to contain power, you have to consider some trading with operating frequency as well. Then static power, not much can be done, but still we have ways and means of how the sub-threshold current could be controlled, and to what an extent VDD can be scaled down. Then short circuit power dissipation can also be controlled to a small extent. So you have different techniques like clock gating, using sleep mode configurations for reducing the transition activity. You can scale the transistor sizes. You can even think of reducing the interconnect sizes which are used, so that becomes one of the aspects of how the capacitive load can be reduced. Then suitable lowest VDD could be used, and then if you think of static power, then selectively use ratioed circuits. Not all should be ratioed, but some may be ratioed, some may not be. So depending upon that, for which you may also use different threshold voltages for different transistors in the crucial paths. Then leakage reduction can be done with the stacked configuration by using body bias, because body bias means threshold voltage is directly related to body bias, and if that is used to an extent, you can control the leakage. Then temperature could be another parameter. So why at all do we talk about low power design? Why at all should we go in for low power design? So it is essential because your contemporary high performance processors, they consume lot of power, and therefore if we go into using low power methodologies, we are going to reduce the cost of cooling methods, packing methods which are required, and growth rate of portable devices. You see, it is enhancing like anything. Everyone wants to have a palm top and a mobile which is very small. So that means there is demand from the public, from the customer. Then battery life is very, very important. Not so much of research or advancements have gone into battery life enhancement, as is the speed in with which the different design techniques have improved in VLSI design, and therefore still there is a lot of gap between the battery life usage and the design, and therefore everyone wants to have the best battery, longer battery life. So from that point of view, low power designs would definitely give an edge. Then commercial success of these products depends upon weight, cost, and battery life. And low power design methodologies is important to make all your e-gadgets commercially economically viable. Then there are other high performance design techniques which could be at system level, algorithmic level, software based methods, as algorithms are directly controlled by software related techniques. Then architectural level, you can go in for parallel processing, pipeline processing, then redundancy, data encoding. These are some of the techniques which actually go into at architectural level. Then process dependent low power techniques, we have already talked about voltage scaling and variable or multiple threshold CMOS designs. Then at gate level, we can restructure the logic, we can restructure the input reordering, and at transistor level, active power management, leakage management, then transistor stacking, transistor sizing, dynamic body biasing, non-minimum channel length. Usually channel lengths are always kept minimum. That is, if for any technology, if the minimum feature size is lambda, your channel length would be 2 lambda or equal to whatever is the technology. But you can change this, particularly this is useful for analog VLSI design. And to summarize, we have seen that in VLSI design, MOS transistors or devices as well as interconnects, they play important role in the overall performance estimation as technology scales down to a very large extent in to nanometer regimes. Hence, various different research areas come to forefront, which could be seen like this. So research is taking place in static and dynamic digital VLSI design areas, then interconnect design and modeling, analog VLSI design, very, very important area where you talk about all different amplifiers, operational amplifiers. then low power VLSI design and modeling, particularly for biomedical applications, then nanoelectronics, then characterization of small geometry MOS devices, sub-threshold characterization and its applications both at the device level and in the interconnect design level, then characterization of double gate MOSFETs, FinFETs, multi-gate FETs, memristors. These are alternatives coming up to replace the conventional MOS transistors in order to improve the performance of the devices, but obviously it will be at the cost of something. Performance in any aspect in any device comes at the cost of some other parameter, maybe its area or some other. You have to design that at the cost of some other parameter. So you people, I'm sure you must be working in one or the other areas out of these for your research or for your MTech thesis, for your PhD dissertations or thesis, and could take up any of these areas if you are still planning to, and we look forward for more interactions with you all in coming times. So let me conclude what we have discussed in this particular session. So we have talked about VLSI technology, which has scaled exponentially from submicron to very, very deep submicron or nanometer regimes, and it is because of the MOSFET having the feasibility of scaling that all this has been feasible or possible. Then MOS devices and interconnects are equally important when we talk of very large scale integrated circuits, and the chips or the in general when we talk about an integrated circuit we call it as a chip, and it is housing large systems which gives easy portability to the device, actually to the overall electronic gadget which is using that particular integrated circuit. So the very aim of VLSI in today's scenario is low power and high performance, so as to make human life more comfortable and worth living. And chips or the integrated circuits, they are finding application in every electronic gadget in whichever sphere of technology you may think of, be it space, automobiles, multimedia, internet, or mobile computing, anything you can think of under the sun where electronics is associated, you cannot do without VLSI design. And consequently, the design issues in high performance VLSI integrated circuits are important and have been dealt with in this particular session. Thank you very much, and I look forward for any queries and questions for the interactive session which we can have now. These are some of the references which are quite important, and you can take a note of them. ITRS is one which, so now it is ITRS 12 actually instead of 2001. I should have mentioned 12 here. And Vesti, Shragian, Kang and Leblebisi, these are some of the books which have become very, very relevant books for this particular area. Then different books on low power by Keep and Pedram can also be looked into. If you are working with SPICE, then Robert, Sidra and Smith, and book by H.M. Rashid on SPICE are very, very important. R. Raghuram gives a very good aspect of modeling electronic circuits actually. We have to know the entire MOS modeling, the electronic device modeling before we can enter into VLSI design. Because after all, we are not doing anything manually when we talk of VLSI. We have to do everything, or everything should be automated. Just like every fabrication part is automated, every design part also has to be automated when the number of components becomes very huge, and as a result of that you need to use some softwares which should come handy to you in order to see the performance of the circuits and systems before actually you go in for fabrication of those, so as to make a foolproof troubleshooted trouble free circuit, so that you encounter minimum losses when you fabricate anything. Then you cannot change. That is the only drawback with integrated circuits, that once fabricated you are not in a position to rectify it. So you have to rectify it, you have to bring in the testing features which I have not touched in this talk. The testability and automation of the design comes into the chip from the very beginning. When you are designing a circuit, when you are designing a system, from that particular point itself, the testing reliability issues, they are built into the integrated circuit, and that itself makes it designed for test or DFT, and testability is possible. So these are other important research areas actually of VLSI design, where testing and testability are a part of it. So for all this you need to have a good understanding of device modeling before you go in for VLSI digital design or analog design. So thank you very much for this session, and I look forward for some interactive session with I look forward for interaction with the participants of different institutes, please.
Good afternoon, ma'am.
Yes, good afternoon.
I am from Madan Mohan Malviya University of Technology.
Yes.
Ma'am, Madan Mohan Malviya University of Technology.
Okay, okay.
Ma'am, you have shown the equation of tau PHL and tau PLH in one of your slides.
Yes.
My question is that are these equations possible for the fully depleted SOI MOSFET? Same equations.
See, for fully depleted SOI MOSFETs, the functioning is the overall functioning or overall what we are expecting. The IV characteristics look very identical, but still you have to look into that which all parameters become different as compared to the MOS conventional MOS transistor in case of fully depleted SOI MOSFET. So once if you know the device modeling of SOI MOSFET, then you can use that current equation instead of the conventional MOS current equation which we have used for deriving the tau PHL or tau PLH. So it means that if you are clear about the device modeling of SOI MOSFET, then it will be as same as this.
Okay, thank you.
Welcome.
There is a question from JSS Noida.
Yes.
How can we increase the performance of the VLSI circuits?
How can we increase the performance of VLSI circuits? See, when we talk about increasing the performance, we have to keep in mind which parameter are we aiming at. Are we aiming at delay-centric design? Are we aiming at power-centric design? Or are we aiming at an optimal design? Out of this, it will be a deciding factor whether you are you want to trade area, you want to trade delay, you want to trade power, or you are looking forward for an optimal design, which is actually the main requirement is an optimization. So different optimization techniques can be used along with the design techniques in order to get the most optimal result, in order to get a high performance output. Yes, please. Good afternoon.
My question is, can we analyze a circuit which is designed by CMOS circuit using S parameter?
Can we design? I could not get you the first part.
Can we analyze a circuit designed by CMOS using S parameter, static parameter?
Okay. See, many of these circuits which are taken up in RF CMOS design, that is radio frequency CMOS design. Their S parameters will become very handy, because I'm sure in RF CMOS design they are using S parameters as one of the techniques to analyze the circuits. So from that point of view, yes, you can.
And while using S parameter, we consider some reflection of power actually.
Yes.
So, do we consider reflection of power while using for low frequency signals?
See, we are using reflection of power particularly in interconnect design. From circuit or device point of view, I have not worked much on this area, but when we talk of interconnects, particularly global interconnect design, there we talk about reflection of signals because of the inherent inductive, resistive and capacitive effects associated in interconnects. So from that point of view, yes, we do consider that particular parameter, but you have to rather we have to study more in detail about how it will be affecting the devices. We are not getting your voice, please. Still your voice is not hearable at our studio.
Good afternoon, ma'am.
Good afternoon.
Yes, ma'am. I'm from MIT Muradabad. Yes, you defined a dynamic and switching power that is a factor alpha.
Yes.
How can we reduce that factor alpha? That you explain reduce the VDD or the some other terms. But what is this alpha? Alpha is you say that is a. How can we reduce it?
Yeah, alpha is switching activity factor or transition factor, and it plays a very significant role, particularly in digital circuits. So you see, a digital circuit or a digital gate, we can configure it in different ways. We can configure it in different by using different design techniques, so that the switching activity or how many gates they change from 0 to 1 or 1 to 0. That is what actually transition activity is. So by reordering the inputs or by taking different way of designing a logic circuit, you can reduce the switching activity, and that is actually done in order to reduce or contain the dynamic power.
Now, for a particular circuit that is a constant, a NAND gate, its output is constant. So how can we?
See, we are not talking about very small circuits. When you take simply 2 input, 3 input NAND gate or an inverter, in that circuits you may not be able to identify these. Typically, when you talk of even if you talk of dynamic circuit, for example, dynamic circuits, you try to do away with the PMOS logic and just use one PMOS transistor in order to enhance its speed. But if you, in that case also, if you take a small circuit, जैसे आप NAND gate लेते हैं, and if you take an inverter and if you try to see that okay, my power dissipation should be low and delay should be low as compared to static, you will never get to understand that yes, we are in a position to do that. Rather उसमें क्या होता है, ज़्यादा हो जाती है in the beginning when the circuit is very small. So for a bigger circuit, when you are designing a complete ALU, then in that case you will be in a position to reorder, to rearrange so as to get a different critical path. Critical paths can be different by designing, by taking different design techniques. From that point of view, you have to think, not from small circuits.
Thank you.
Hello, ma'am.
Hello.
Ma'am, this is Kantarova from Guru Tegh Bahadur Engineering College.
Okay.
Delhi. Ma'am, I have a question regarding VLSI testing. The question is, ma'am, the power dissipation, the test data and the power consumption of a circuit can be reduced through VLSI testing. Is it possible, and what are the techniques for that?
See, testing is an entirely different research area in VLSI, and one method is IDDQ testing. Other methods are like your scan tests and DFT tests, designed for testabilities, which actually are taken into account when you are suppose designing a complete processor or an embedded system. In that case, you will not be in a position to identify the errors or problems which come in a design. So from that point of view, testing is area which actually can be taken care of, included in the design from the very beginning, so as to have certain patterns, certain signatures of the circuit which is fault free, and signature of the circuits which are compared if it is a faulty one, and if there is a difference in those signatures, then you can identify, because when you are designing a very huge circuit, you will have n number of terminals, you will have n number of inputs, say. So in that, it is not possible to test each and every combination. So what is done is automatic test pattern generation is done, in which it is ensured that the signatures are actually compared to diagnose the health of the complete system which is designed.
Ma'am, one more thing is there. We have a hold flag over here which we use.
What do we do?
Hold flag. Using hold flag, we try to compress the data and try power dissipation also get low. Is it possible by that?
See, I'm not much into doing research in this particular area. To an extent, it can be, but I'm not the right person to answer this query, please.
Okay, ma'am. Is it possible through using VLSI circuits like MOS circuits also?
Could you repeat the question?
Is it possible by using MOS circuits?
What is possible?
Reducing that power dissipation and all?
Yes, of course, MOS. We have talked about MOS circuits, CMOS circuits, NMOS circuits in this particular session, and it is surely is possible.
Okay, thank you, ma'am.
Welcome.
Good afternoon, ma'am. Can you hear me?
Good afternoon.
I'm Dr. Rajiv Sharma from Northern Engineering College, Shastri Bagh, New Delhi. And
Yes.
My question is, when we talk of MOSFET scaling,
yes,
important thing you've discussed is that L should be equal to 2 lambda.
Okay.
So how do we justify that, or how we defend that if we ask how and why? Why the L
Okay.
should be-
Okay, it's in fact my pleasure to interact with so many institutes, so many faculty members in one go. And see, your question is very important for any VLSI designer. First of all, we have to understand what is lambda. So lambda is minimum feature size. For example, if we have technology of 100 nanometer, lambda would be technology by 2, that is 50 nanometer. Okay, so now in general, the minimum feature size we consider is 2 lambda for any design. And why do we consider it as 2 lambda is from this point of view, that the fabrication or the technology would support designing of lambda as minimum feature size.
Yes.
However, if you see any transistor, if we have to form any integrated circuit, it takes a number of masks, actually, number of processing steps, primary and secondary, which go into the fabrication of the complete integrated circuit. So during the fabrication, you actually align your wafer with those masks which represent different layers. For example, active layer or formation of the N plus regions of the transistor or P plus regions of the transistor, formation of the metal layer in a transistor, oxidation. So number of oxidation steps will be required at each time. Each time you are aligning one mask with the wafer. So in this, but even if it is automated, there can be some misalignment. There can be an alignment error. So we consider that at least it can be to the tune of 1 lambda. So in order to take into account the alignment errors, we keep the minimum feature size as 2 lambda, so that no problem actually occurs when a complete integrated circuit is formed due to this particular reason.
In a very broad sense, we can say that it is primarily dependent on, it talks about the alignment accuracy.
Yeah.
Okay, ma'am. Thank you. Thanks.
Okay, okay. Any more questions, please? My in-house students also, if you have any queries or questions, please come up. Yes.
Consider only load capacitance effect. We are taking TPL is equal to CL by mu and CX, WL by VGS minus VT. Now we have to take gate to source capacitance, that will be parallel with load capacitance. At that time, the overall capacitance effect will be raised. At that time, load to high transition will take more than time.
See, in this expression, I have given you a very overview of things. I have not gone into the depth of anything. Okay, so when you talk of propagation delay, the two constituents of the propagation delay at the rising edge and the falling edge, in that case, rise time and fall time are considered, but when we talk of the capacitive load, when we talk of the load, CL which I have taken is not merely the capacitance seen at the output. It will have many components. It will have, say, the output capacitance seen for the circuit for which you are trying to find out the propagation delay. It will also see the interconnect capacitance which is joining that gate to the fan out. It will also see the input capacitance of the fan out circuit. So that means your CL has three components: C in plus C int plus C out. Okay, so there, now which capacitances form that C out of the complete circuit will be important. Now when we say that we want load capacitance to be contained in order to contain the power delay. So in that case, we will actually have to go into device scaling, MOS scaling, or transistor sizing, what is it is known as, so as to contain those capacitances which will be forming the output or the input capacitance of the circuit, so as to bring down that overall CL value. Likewise, we said that in interconnects also we have different methods by which we can decrease the overall interconnect equivalent capacitance. So those methods need to be treated and taken up in order to contain the value of the load. Okay, thank you very much all the participants for this technical session. Once again, I thank Dr. Rajesh Mehra and his team of NITTTR for having invited me here. I hope you all enjoyed the session. Thank you very much.
Thank you very much, ma'am, for this very nice presentation on high performance VLSI design. It was really very informative, and I hope if anyone is interested in doing their research in the area of VLSI design, so ma'am has opened so many areas. She has given so many means list of research areas, so you can take up any one of those areas and then you can start your research. So I hope this session was really nice, and we are really thankful to ma'am for giving answer to each and every query so patiently, because 24 centers are basically connected here in this STC, so a lot of queries are there, and it is really a pleasure for us so that we can clarify as much as that we can. So now we end up our morning session here, and it is time for lunch. So we will be back at 2:30 sharp. So I means close this session and enjoy your lunch. Thank you. Please.
Hmm? No, no.
नमस्कार भाई साहब एक कार्यकाल में अपने अखबार में काम करते हैं अजय क्या नाम है अजय यार उनका नंबर देना और 8930 899 बात हो गई भाई साहब बात हो गई अभी कॉल करवाओ
सारे बंद हो गए बढ़िया यहाँ पे से पता ये नहीं होता
चले एकदम। आपकी एडजस्टमेंट लैब किसकी थी?
किसकी?
किसी की?
हाँ।
कौन कराएगा उसे?
मैं।
तो मुझे भी बैठा रखा है वहाँ।
क्यों? तुम तो उसमें थे एस्टेट में। तो मुझे एचओडी ने काम दिया नहीं था। दूसरा कहाँ से आ रहा हूँ? सब फैकल्टी वो करके फिर एग्जाम चल गया, फिर उससे कैंची ऐंची लेके सारे फोटो चिपका के आए।
तो चिपकाने के लिए कैंची की जरूरत क्या पड़ी?
एक पेज का फॉर्म नहीं है, एक पेज में 6 नाम है, इतनी इतनी जगह छोड़ के।
तो ऐसे बता रहा हूँ ना, फोटो काटने के बाद चिपकाई।
तब नेट चला, किस पे चल रहा है?
नेट पे चलना। रुको रुको रुको, क्या करना पहले ये बताओ।
तीस आईपी कहाँ यूज करे आपने?
ऐसा 30 मिले कहाँ है?
अरे 25 भी यूज नहीं हो रहे, 20 भी यूज नहीं हो रहे, 20 में से 0 और 2 भी यूज नहीं हो रहे। टाइमिंग बताओ, टाइमिंग क्या है?
किसकी है?
मैडम और आएंगे we have to हमारा इंट्रोडक्शन बराबर वाली लेंथ दीजिए एक नंबर है सर
कोई ना अभी
Good afternoon to everyone. Welcome to our third session of the day. Again, Dr. Rajivan Chandel is with us. So I invite ma'am for a talk on VLSI interconnection design issues.
Thank you, and I welcome you all to this third session of the day. I welcome all the participants from all the 24 institutes for this session. We'll talk in this session on VLSI interconnects and some design issues associated with VLSI interconnects. In the morning, we saw how MOS devices, how CMOS devices, they are handled, what are the issues related to them, what are the main parameters which are related to the CMOS devices, how they can be controlled to enhance the performance of the devices and circuits in particular. But we have to remember that when we are talking about huge chip complexity. Chip complexity means huge number of components per chip. Then these components need connection. They need connection between each other, and for that interconnects or interconnections play a very major role. And let us see how these affect the overall performance of the device, how these are to be handled, what are the different techniques used for VLSI interconnects. In fact, my area of research has been VLSI interconnects, and the topic is very close to my heart. So in short, we will be talking about introduction, then design issues and high performance solutions for VLSI interconnects, carbon-based materials as alternatives for these, different signaling techniques which can enhance the performance of the circuits, then variability analysis, some case studies will be dealt with, and finally we'll conclude and give some references. So let me introduce you. Just like in the morning, we again remember Gordon Moore whenever we start with VLSI or anything related to it. So the number of active transistors on silicon integrated circuit would double every 12 months, and the prediction of 6,000 components on a single die would be possible by 75, and these have all stood true all these years. And let us see why this has been possible. So in the morning we did discuss about dimensions to an extent. So 9 is a very important magical figure in VLSI in the present era, and device dimensions are all in nanometers, so that is 10 raised to power minus 9 meters, and number of devices on a chip range from 10 raised to power 9. Then this is nano regime, and if you see the picture down here, this particular graph, you will see a very huge area of this region of this circle, which is corresponding to interconnects. So this is because the interconnects play a very major role. Interconnects, they occupy a very huge area in a VLSI chip. It is almost 65%. You will see blue color, dark blue color, 21%. That is related to clock. That is again related to the interconnects only. This means the signal, the data, and information, power, as well as ground lines, they have to run all through the chip, and as a result they will occupy the maximum area, and therefore research and technical know-how on interconnects is equally important as the CMOS devices. Then 9% is the I/O, that is the input-output peripherals. Only 5% is CLB, that is configurable logic blocks, or the basic logic circuitry in a VLSI chip. That houses only 5%, and the rest of it is all what is the main portion of the chip, and out of that interconnects lead to very important part in the chip, and therefore it becomes a very major area when we talk about VLSI circuits. We have shown this in the morning also, and here you can see very clearly the different Intel processors actually. Started with microprocessors 80, 85, 86, then 286, 386. These are all Pentium machines, and then they have gone up to Xeon, Core Duo, and Core i7 and all that. So they have shown that how with the advancements, the number of components per chip, they have enhanced over the years. Now let us look at this figure. You can see huge amount of wires. So it is a look of an early computer and the interconnections which will be required to join all the components at that time. So the aim had been to minimize or to make the system in such a way that the system overall dimensions are reduced, this wiring is done away with, and everything is more automated, more convenient to be handled. And in 50s the PCB technology became widespread, and you all must have seen such type of PCBs where these lines actually show you the interconnections which will be required to join to connect the different components. Then came the backplane designing, which became more popular, and you can see that within particular block you will have the backplanes, and further the different modules will be connected between the cabinets, and this is a wider view of the same. Now let us see, we are interested in on-chip interconnects rather than off-chip interconnects which were shown earlier. So on-chip interconnects means how you have to connect the different components. Now the chip area, maximum chip area says 1 inch by 1 inch or slightly more than that. When we have that particular area, it's a very huge area in terms of nanoscales and nanometers, but still there is a limit on how many components you will be in position to connect on this at the silicon level. That means at the level which is very close to the semiconductor. So that becomes the nearest or the innermost level. But however, the problem is that if you connect different components at that level, the complexity of the interconnects will be so high, and if you take metal interconnects, there will be so much of interference between the signals which are passing in those interconnects that it will be difficult to handle the crosstalk and the other noise which will get associated, and we will not be in a position to actually see the right signals at the right points. Because of that, different levels of metallization are actually used to overcome the density of the interconnects in one level. So as a result of that, you have different planes, see, first plane, second plane, third plane, vertical interplane interconnects are shown, in which you have one layer of say this is the devices or the semiconductor, then you have small interconnections which are very close next to the semiconductor, then you have you can say insulator in between, then you have the metals, so it will be more clear here. So you have say level locals 2, so you have level 1 and then very close to this level 1 and then level 2. So this level has these particular interconnections with these active components on the semiconductor. Actually all the connections which will be made are to connect with the semiconductor. So it is not possible to house all the interconnects in one level. As a result, you have in between metals, then oxide or insulator so as to isolate the layers. Then you have another metal level, you have again dielectric capping, then wiring. So if you connect something from here to this level, so in between you will require deep trenches sort of features which are termed as vias. So the one which is very close to this, like this will be termed as a contact, metal contact. And if you are connecting one metal wire to another metal wire and then through that to another metal wire and then finally coming to the chip, that is termed as a via. Otherwise the concept is same, that it is sort of a window which is created so that the metal can flow from that layer to the next bottom layer. So this is scanning beam electron microscope photo of a local level interconnect which is seen, and these show the active part, green parts, and these show the via, and the yellow one is the metal. So metal has to be connected with the active region, so that is where you will require that contact part. Again you see these in different perspective. So you have the logic or the distributed memory, repeaters, analog or RF design, optical devices. So this is actually schematic of a 3D IC and 3D integration with multi-level wiring networks, which are being shown here in this particular figure. So all the connections actually which are to be made are with this semiconductor which is required. Now let us come to another era of materials. So other than metal, because metals have their own problems associated when we go to the nanoscale regimes. Something called electromigration. That is one of the major problems associated with metallic interconnects. When there is surge current or say very high current density, current per unit area, then that can lead to either blockage or short circuiting or open circuiting a particular metal. So complete transfer of metal from one portion to the other is termed as electromigration, and as a result of that we may develop short circuits or open circuits in the integrated circuit, which will make the chip actually malfunction or unusable. And as a result of that, alternative materials are being sought for in terms of graphene or carbon nanomaterials, in terms of carbon nanotubes, and graphene nanoribbon interconnects can also be used, and a lot of research is being carried out. On one part is the study of these. On the second part is how to make fabrication of silicon compatible with these particular different materials, because you all know that whenever we have different material, for example, if we talk about silicon, if we talk about germanium, and thirdly we talk about gallium arsenide, all three materials have different technology actually entirely to handle these materials, even though they are all semiconductors. So similarly, if we are talking about an entirely different material, then again it has to be compatible actually on the level of fabrication. So those are the issues related to these. This is something related to wafer dimensions, which we said in the morning also, that like half an inch or 2-inch wafers were very common during 70s, 80s, but now we have very huge wafers. You can see this is the diameter in centimeters square, so you can well imagine that what will be the sizes of these. So typically 12-inch wafers are what is available practically today in industry, and it is because of these. So 12-inch wafer means in this on this type of wafers only you will be able to develop VLSI chips or ultra large scale integration chips, which will require at least slightly more than 1 inch by 1 inch area. Okay, so this means that if you are having say 1 inch by 1 inch chips, you will be in a position to get appreciably say 10 to 20 or so such a number of wafers in one go, because VLSI fabrication is all mass fabrication. You don't make one chip at a time, you make thousands and thousands of chips simultaneously. Same processing, same techniques, same flow is used for small scale, medium scale integration, large scale integration chips. Could you give an example of medium or large scale integration chips or small scale integration chips? It would be in the form of, say, the most common ICs which you see in the labs. For example, your 555 timers, your 741 ICs, op-amps, right? So those are the chips which are commonly used in lab, and the typical cost of these would be, or your gates, different types of gates, 7402, 7404, these type of chips would not cost more than a rupee or so, or 5 rupees or so per chip. But same technique is making processor, Intel processor, and it costs in thousands, or such a big number, such a big margin between the cost of similarly produced chips. It is because of, basically because of the yield ratio. That means you are mass fabricating huge number of chips in small scale. The number will be very large. Thousands of them will be produced simultaneously. In thousands, if 100 out of them are not good, even then the yield ratio, that is good chips divided by the total number of chips into 100, will be very high. That is, the yield will be very high, say 96 to 98%, and therefore cost is directly proportional to yield ratio. Therefore the cost will be low as the yield ratio will be very high. It is sort of inversely proportional. If yield is high, cost will be less. And in case of the VLSI chips, the yield is less because you are producing, say, 10, 20 or 100 chips in one fabrication go. If 6 or 10 out of them are not good, then as compared to 10,000 where 10 were not good or 100 were not good, this brings down the yield ratio immediately, and as a result the cost shoots up. And otherwise it is the same material which is being used for the fabrication of the two. This is another way of looking at how the things are reducing in dimensions. You can see from here some typically biological cells, then bacteria, then here diameter, virus, nerve fibers, and like that you can come to a scale from 1 centimeter to, say, 10 nanometer, which is reflecting a DNA for comparison of how these scales are actually when we are talking about nanoscales and all. So local lines scale, that means we have three categories of interconnects basically. The ones which are very close to the semiconductor, which are connecting transistors at the lowermost level, they are treated as local interconnects, which will be quite small because the components are quite small and you have to connect them, so they will be termed as small scale or local interconnects or small interconnects. And the ones which are passing your VDD line, that is supply voltage or the ground or the clock signals to the entire chip, so that means they are traversing the entire length of the chip, so those are treated as global interconnects, and usually they are the topmost level. If you have, say, 9 levels of interconnects, they will be at the topmost or one below level interconnects. All between the small scale and the global are treated as intermediate interconnects. So they will have properties which are in between the two type of interconnects. So when we talk about the local interconnects, they have similar behavior as a scaled down MOS device would have. In a scaled down MOS device, there is decrease in resistance, you can say, decrease in parameters which lead to decrease in delay, decrease in power. So similarly local interconnects will reflect the same behavior. We have talked about minimum feature size lambda, and we said that if we have to compare a CMOS device in terms of lambda, we compare the channel length, which is usually twice the lambda dimension, where lambda becomes a pseudo parameter of dimension, and depending upon technology you can associate a length with it. Similarly, when we talk about local interconnects, they will also have minimum dimension or minimum length, which is reflecting the minimum feature size. So this is the only interconnect which will be associated with minimum feature size. So different non-ideal effects actually get associated at scaled dimensions. So we have talked about electromigration. So it is because of the grain boundaries, the surface boundaries associated with the metal or with the line which is passing the signal, and because of these electromigration actually takes place. That is the reason why. So if you remember, even if we talk about metal, or even if we talk about, it will be more convenient to understand that we take polysilicon as gate instead of metal. So MOS is replaced, M is replaced by polysilicon. So polysilicon, it is more easier to understand in terms of polysilicon and silicon. So the main difference is silicon is crystalline in nature and polycrystalline is not. It is amorphous. So that means it will not have a continuous structure, crystalline structure. It will be having grain boundaries of this type. Small regions will be crystalline, but entire will not be, and as a result these boundaries will come into picture. And if boundaries are there, and if there is a surge current or huge current, there is a chance that the entire material from one portion may shift, traverse to the other, like this. So one interconnect which is passing a huge current may land up in a hillock type of transfer of material, and thereby short circuiting two lines. So like that you can understand it. So it also leads to voids. So for example, if you have transfer of material, it can lead to sort of gap between this. So void formation could be there, which is again not wanted, and this is again associated with the with sort of non-ideal characteristics which are associated with metallic interconnects. So this shows you the silicon material where you have very local interconnects associated with it. Then in between you will have number of interconnect levels. He is showing metal 6, metal 7. In between the metals is all dielectric, metal 8, and something here, that is what is shown as a humor, but excessive heat or electromigration, that will lead to such type of excessive heat and power dissipation, which actually leads to electromigration. Okay, so now another non-ideal effect than this particular problem is the problem of jitter and clock skew, which may be associated. That means the difference, say delay between the two signals could be there. So clock reaching at a slightly faster point as compared to the same clock reaching at a slightly different timing at some other place, which is not desired, or within one signal. So these are two signals being compared at 2 points, or you can compare within a signal. It may, one may reach at this point, the other may reach at this point. So these lead to skew and jitter problems with metal interconnects. So possible solutions to these interconnect quality issues actually are say replacing dielectric with air gap structures. It is very easy to say than to do, because bringing in air gap structures is not that easy a job as compared to metal, as compared to dielectric materials which are actually placed in these chips. Then replacing copper with new technologies is what is being researched into very extensively, that as nanowires in terms of your carbon nanotubes or graphene nanoribbons, then optical interconnects to get the advantage of very huge bandwidth then wireless interconnects, then superconductors, so as to mitigate the problems associated with parasitic components which are associated with any line. So what is a interconnect? It is a basically you can say a three-dimensional structure, a cuboidal structure, which will have certain length, certain width and certain height, and it is made of some material, some metal like aluminium or copper, and as a result it will have some resistivity associated with that material. So resistance is bound to be associated with that material in form of rho L by A.
We are not able to hear you. Can you remove noise?
So likewise, you will have capacitance associated with the interconnects because of the presence of two conducting metals and dielectric in between them. So whenever such a structure is there, you are bound to have capacitance, that is epsilon A by Tox or D, that is this distance between the two. So such type of components, parasitic components, and similarly if the length of the interconnect is very huge, or if the frequency of operation is huge, then inductance is also coming into picture, or it will also crop up. So all these are L and C components which are unwanted components coming on their own because of the dimensions of interconnects or because of the material properties. Actually they lead to various non-ideal effects, and the designer's job is to mitigate those non-ideal effects. So these alternative materials is one option which is actually being thought of, that how to use it so as to mitigate these materials. Other than this, different signaling techniques like you have voltage mode and current mode signaling techniques. We'll just see little more in detail how these are taking place. Let's see the carbon based material interconnects first, which provide a solution for high performance. Actually, if it is possible, if it becomes possible in days to come, in years to come, to actually fabricate carbon nanotubes along with the silicon, it will be a milestone achieved in electronic industry, which will actually take the, just like BiCMOS. In BiCMOS technology, you take the advantages of BJT, bipolar junction, bipolar technology, and you take the advantages of MOS technology and fabricate both bipolar and CMOS devices or MOS devices in one integrated circuit. So BJTs give you, BJTs always have very high performance because these are exponentially controlled devices. IV characteristics are exponentially controlled, whereas in MOS this obeys a square law behavior or square characteristics if you see overall performance. So BJTs having an exponential behavior have a very high transconductance, that is change in the current by change in the input voltage, output current by input voltage. So if you check that, that is very high in case of BJTs, and your gain or your speed gain is particularly directly proportional to transconductance. As a result, BJTs have a very high gain, very high speed, and which MOSFETs don't. But on the other hand, MOSFETs have feasibility for scaling down, feasibility for a CMOS structure, and as a result of that, you can have an upper hand in terms of power saving in MOS devices. You have an upper hand in terms of high input impedance. So if you are having a BiCMOS technology, you are using the main advantages associated with MOS devices, and in the output stages you are using the main advantages of the BJT technology. So likewise, if it becomes feasible to integrate these technologies, carbon nano-based graphene material with silicon, it will do wonders in times to come. Let us see some of the more details about this. So carbon-based materials include both CNTs and graphene nanoribbons, and they have high current carrying capability, remarkable physical properties, high mean free path, long ballistic transport length, and high thermal conductivity, high mechanical and thermal stability. So these are in comparison with metallic interconnects. So obviously if any material has such good properties, it would be definitely a better alternative for interconnections in the integrated circuits, for making them more reliable, more secure devices. When we talk of carbon nanotubes, these have different arrangements, you can say. So this is a single wall carbon nanotube. Then that means only one tube associated with this. This is a bundle actually of a number of such single wall. Then this is a multiple wall, where you can see a number of coaxial carbon nanotube tubes being within one tube. So that becomes a multi-wall CNT tube, and again taking its bundle and studying it becomes important. So this is how they have shown the different dimensions which are actually used to show one bundle, one tube. Then you have mixed wall CNT bundles, where you can have this multi-wall CNT and single wall CNT in some configuration associated with one interconnect actually. So the behavior of looking into the interconnect is that we have to give an electrical equivalent model. Just as we do that for any MOS device or any bipolar device, any PN junction diode for example, you have to represent it with an equivalent electrical circuit. Because we said in the morning, we actually use different automation tools, EDA tools, electronic design automation tools, to study huge circuits. It is not possible to develop a circuit manually on the breadboard and see if the number of components are more than even 100. It becomes very cumbersome with huge wiring between that. So therefore EDA tools become handy in that. But what is an EDA tool basically? It is somehow understanding that a particular device is a MOSFET, particular device is a BJT, or another device is a diode, and like that. So that means some common modeling has to be done. So what is that? That is giving an electrical equivalent circuit to all the components, so that they are able to identify that this EDA tool is able to identify that what is being studied, what is being used. Okay, so likewise the electrical equivalent model has to be given for all structures, and this is how it is given for a CNT interconnect. Now let us see some of the case studies. So this is a case study in which you have a driver, which is again a CMOS buffer is being used, or you can use a CNT FET buffer using CNT FETs, or you can use any alternative materials. But when we are researching and studying them at our place or by anybody, it is very easy. But the main problem which is being faced today in fabrication or real commercial development of these is how the two technologies are to be made compatible. Okay, that is to be kept in mind. So here is an interconnect which is CNT in nature, which could be metallic interconnect or it could be CNT interconnect. So different behavior of different such materials are to be studied and seen. So these are some of the properties based on ITRS, that is International Technology Roadmap for Semiconductors. Just write ITRS in your Google search and you will get a lot of data related to that, which is very important for any VLSI student. Corresponding to these this particular data, different parameters that is the equivalent model structure, which is looking into what will be the resistance, contact resistance, what will be the inductive components associated, self-inductance or mutual inductance, then quantum capacitance, electrostatic capacitances, coupling capacitances associated with these different type of interconnects can be studied and seen, and then the behavior can be analyzed for these. So this is some of the analysis which shows that okay, if we are using the copper or the metal interconnects, the propagation delay is the highest, that is shown by the red dots. Likewise, if you take mixed CNT bundle, mixed means it has both mixed wall and this single wall bundles, so they will, that actually shows the best performance in terms of propagation delay. Likewise, so this was with respect to rise time variation, and this is with respect to power supply variation. So again you see that the copper interconnect, it shows the worst behavior, you can say, in comparison to any of the CNT interconnects which are taken as alternatives. If you come to the power dissipation, again copper shows maximum power dissipation as compared to any of the interconnects, any of the CNT interconnects, which are having an upper hand both in terms of delay and power dissipation. So this is actually work done by one of my PhD scholar, and the work is still under review by IETE. In this second case study, I am showing you the equivalent model of two interconnect lines which are actually driven by a buffer, and at the output also you see a buffer which is acting as the receiver with some capacitive load, and then some coupling capacitance has been shown here, and individual so you will have to model it as a distributed line with huge number of such sections depending upon the length of the line, and then you have to analyze this. For example, if you are taking this as A line and this as B line, let us see the behavior that if I give a signal here, say rising from 0 to 1, and on this if I give 0 to 1 rising signal, it means in phase signals are given, and if I give in this 1 to 0, it means out of phase signal is being given. And then for this out of phase signal, these are two actually independent lines. If I am giving something here, it should not affect this line if this is, let's say, at ground, or if but that does not happen. If I am keeping this even at ground and giving something here, that output should have been reflected at V out 1, but it also reflects at V out 2, because there will be some amount of coupling, inductive as well as capacitive coupling between the lines, which actually leads to this crosstalk type of effect or noise in the other line. You can call one as the aggressor line, other as the victim line, and like that we can study. So this shows you when both are switching in the same direction, then how the voltage, which actually should have been at this level, it tends to increase or decrease if you are taking level 1 or level 0. Both have been shown in this with transition time. If you vary the transition time, then how would it behave? So at lower transition values, transition time values, that is tau r and tau f, if these are low, it is very prominent, the switch in this cross noise is very prominently seen in an interconnect. Likewise, another way of reducing this crosstalk is by using number of repeaters. Repeaters means that I divide this line in a number of sections. For example, let us consider an example that if I have an interconnect line which is having 5 units of capacitance associated with it and 5 units of resistance associated with it. So overall, the product of resistance and capacitance is a measure of delay. RC product gives a measure of delay. So that line will have a delay of 25 units. And if I divide that line into subsections of 1 unit each, 5 sections of having 1 unit, section having 1 unit of capacitance and 1 unit of resistance, then each one will have 1 unit, and product, sum of these will give you 5 units. Okay, so that means to a large extent the delay can be reduced by dividing a line. And then if you divide a line, obviously you have to get connected, you want a signal to flow through it as a continuous signal, so you will have to incorporate or add buffers in between, so that there is no loading effect also and the signal also passes properly. So as a result of that, you actually are in a position to reduce the delay to a large extent. For this, you can go through some of the papers by J.D. Mendel and Jeffrey Davis. Even my PhD work is associated in this particular area, so you can refer to my papers also. So this work is further carried out by one of my PhD scholars, Gargi, and in that we have seen that if we change the dimension of these repeaters or the buffers which are to be incorporated, then does it have an advantage or does it have a disadvantage? So you can see the black line represents minimum feature size, minimum sized buffers, and the red line shows 10 times the minimum size buffers were placed in the interconnects. But you can see that when the number of optimal number of repeaters which are required, if actually that is less, then middle path would be the best. 5 times gives you the minimum crosstalk. But if the size or the number of interconnect repeaters required is large, then the overall crosstalk actually is quite high if you increase the size of the repeater. So that means increasing the size of the repeater is actually not a very good alternative. It will also consume more area, but likewise minimum sized repeaters may not be good if the optimal number of repeaters is small. So you have to take a trade-off between what is the dimension of the repeater, what is the dimension of the interconnect, what is the optimal number of repeaters required, and according to that make a judicious choice. Let us see another case in which we have taken 3 interconnects and referred 2 as aggressors and 1 as the victim line. So if you see the victim line and the neighboring lines, so this arrow shows that if my signal is changing from 0 to 1 in all the 3, you will get and see effective value of CG. However, if there is a change, one is high, one is low, then you have different values of equivalent capacitances in terms of the gate capacitances and the coupling capacitances. So according to this difference, actually crosstalk or the noise associated will become different. So you can see some of the results here, where noise voltage is being shown with respect to certain length of the interconnect, then aggressor width, that means the width of the your driver, victim driver's width is shown, and you change the width of the interconnect and the spacing between them, and then you try to see that what would be the effect. Obviously, if the width is more and the spacing is more, as in shown by this pink color, that reduces the noise in the two lines. Likewise, here it is shown another case where you have again changed this length, you have changed this actually width of the aggressor, and as a result of that you can again see that the overall crosstalk which is attained, that becomes different, but the behavior remains same, that if you increase the spacing. So that is the crux of the story. That means how big a spacing can be kept between two interconnects. Actually, more the spacing you keep, you're actually utilizing more area of the chip, and as a result lesser number of interconnects are being housed. So you have to maintain an optimal value in which the noise is also contained, area is also optimally used, so that neither it goes waste nor it leads to noise beyond a particular threshold value. Okay. So this is the effect of wire spacing on coupling noise, which is being shown. So peak positive noise voltage and negative noise voltage both have been checked and seen, and you can see that in the blue line is showing for a spacing of 2 micrometers, and the black one shows the green one shows for 8 micrometers. So again the peak noise also reduces if the spacing is enhanced. So this effect is correct for both positive and negative peaks which are obtained. Then you can check with interconnect length. So with interconnect length, again both you have to develop analytical models based on the electrical equivalent models, and then compare your results with SPICE, that how correctly your model actually replicates it. So again peak positive and negative voltages are seen with respect to interconnect length, and as the length increases, overall trend is increase in peak noise voltage, but then it is the spacing which actually contains it to an extent. So you can see these journals which have been published. These are all SCI journals in which Rohit Dhiman has published his work. You can check with them. Parametric sensitivity analysis is one of the very important analysis being carried out, should be carried out for all devices, all interconnects, in which you see what is the behavior of the interconnect when there is PVT variation, that means process, voltage and temperature variations. If these are taken into account, what will be the effect of these variations on the devices, because there will be some variation in the devices. If there is process variation, there will be some mismatch in the two transistors or n number of transistors. So particularly if it is analog design, that mismatch becomes very huge when you are calculating out the transconductances, when you are seeing the behavior of devices which should be totally matched. So we always work with ideal situations, but such type of analysis in which variations are taken into considerations, and then you see that how much will be the variation in the performance. Let us see one more case. This is the last one. If you use different signaling techniques, then what would happen? So that is shown here. You can you see with over the time you can see with National Semiconductors Corporation, from where I have taken this. So you can see that different types of signaling standards for cables and logic families has been there. Like you all must be knowing about emitter coupled logic, then your different ETL logics and all that. So the point is that similarly different types of signaling techniques, just like for logic families, we also have for interconnects, that how the same concept can be used here. So instead of CMOS, TTL, BTL, all these logics, how we can go in for different models. So for this interconnects, we can either go in for voltage signaling technique or current signaling technique. So that is what we will discuss in this. So this is the equivalent model. You have already seen this in the earlier slides also. Now let us see. This is a typical voltage mode driver and receiver, and this is being the equivalent high frequency AC model is being shown in this particular figure, which is also quite known to all of us. Different capacitances get associated, and using all that, then you have to find out what is the input impedance and the output impedance is associated with the device. Similarly, if it is a current mode driver, then your complete driver will have a differential nature, and again you have to compute its high frequency model and determine the input and output capacitances. Similarly, for the receiver side also you have, so the main beauty of this current mode signaling is that you need just the driver and the receiver, and in between is your interconnect. Whereas in voltage mode signaling, you can have the advantage of buffer insertion, but here you do not have that, but it is still having a number of advantages in comparison to the other in terms of different parameters. So these are the methods you can see for determining the overall value, and the major difference you will see is the driver resistance is low and the output receiver impedance is high in case of voltage mode signaling, and it is inverse in case of current mode signaling. RS is high here, RL is low. That makes the entire difference actually in the two signaling techniques. If it is so, then you have different relationships for determining the delay, the energy dissipation of the two. If RL is high, if RN and RS are very high and low value respectively, so you can determine these values and then determine for yourself that okay, what will be the performance of an interconnect if it is voltage mode signaling. So you can see the level. So you have 0.9 here and you just have 0.2. So this becomes a disadvantage. The current mode signaling actually reduces the voltage swing, and you can refer to Yash Agrawal's work. Also some other references we will be telling you, in which he has done work in this particular, he is presently doing PhD work in this particular area. And you can see from this figure that current mode signaling interconnects actually, they have a huge reduction, they see a huge reduction in delay as compared to the SPICE as compared to the voltage mode signaling techniques. Okay, and likewise in power delay product also, your current mode signaling techniques, they lead to better performance as compared to the voltage mode signaling. The dotted line actually shows the model which has been given in 11 reference, and that is by this Bashirullah reference has works on the same. It is in IEEE VLSI transactions. You can see for yourself. So comparison has been made with respect to that and SPICE. So this we have seen. The power delay product is also lower in what does power delay product actually refer to? It refers to energy dissipation in any system. So energy dissipation should be as low as possible. We can compare individual delay, individual power, but one may be low, other may be higher. But if the overall product of power and delay becomes lower, then your purpose is fulfilled. The energy dissipated by that system will be less, and that is what is desired. So this shows you the advantages of the overall current mode signaling. Though the overall voltage swing is lower, but delay becomes reduced, dynamic power dissipation is reduced, power delay product or energy delay product is also improved or lowered, bandwidth improves and throughput also improves. So just at the cost of voltage swing, the other parameters you can benefit if you are using these. Again, parametric variations can be seen or can be verified even for such type of interconnects also, and studied how much is the variation. Another area which we touched in the morning was sub-threshold. So if your circuit is working in sub-threshold regime, or you are trying to build up a circuit or a system for sub-threshold application, biomedical application, then the interconnects would also have to be working in those frequencies, those particular voltage levels, and how will that affect the system. So that can be studied by using the sub-threshold logic. And in that, if you check the overall working of a buffer system only, which will be required for the interconnects, then your red line shows you the sub-threshold, this shows you the power dissipation in super threshold, and the blue line shows you the power dissipation in the sub-threshold regime. So you can well see that their orders are different by 3 times. 3 orders of difference is there in the power dissipation, and that is obvious also. The levels of sub-threshold voltages are below threshold, so obviously it will be quite less and leading to large power advantage. So that can be analyzed and studied, and you can see for yourself these particular things. So you can let us summarize this particular talk. So downsizing of local interconnects and use of long global wires or interconnects in integrated circuits cause various non-ideal effects as well as signal integrity issues which need to be handled. And alternate materials are being looked into other than metals in form of CNTs and graphene nanoribbons to replace them for getting higher performance. Different signaling techniques are being looked into. Then in carbon nanotubes, you can go in for different structures or mixing and mixing up of these single walled and multiple walled, so as to get improved performance in the overall system. Then it is seen that both propagation delay, power dissipation is minimum in mixed wall type of a CNT interconnect as compared to the traditional copper interconnect, which shows the maximum value of delay and power both. Further, we have also seen that current mode signaling technique leads to a lot of advantages as compared to voltage mode signaling technique. And it is also observed that fluctuations caused due to parameter variations or process variations have marginal impact in the performance of current mode signaling techniques as compared to voltage mode signaling techniques. So again, it leads to better advantage. And it is found that downsizing of the scale of the technology causes reduction in propagation delay. However, it adversely increases the power dissipation in a system. So these things need to be handled, and we have seen various case studies to see the overall performance of all these systems which we have taken up in this particular talk. So thank you very much for this session. These are some of the references which you can refer to. So journals like IEEE Transactions on Electron Devices, Journal of Computational Electronics of Springer, then IEEE Transaction on Electromagnetic Compatibility. These also give you some important book by Rohit Dhiman and myself. We have given a complete modeling of interconnects in sub-threshold. You can go through this. It is from Springer. So different then Elsevier journal, microelectronics journal also gives a lot of data about this area. Then IET technical review is one of the SCI journals which also handles quite significant work in both interconnects and MOS devices. So you can make advantage and use your ITRS as well as different free source softwares which are available for working in these areas. So thank you very much for this session, and I welcome you to have an interactive session now. I request all the participants to please carry on with their queries, if any. Hello, we are not able to hear you yet. Yes, please.
Madam, as you said that if we are using polysilicon, in that case, without problem and electromagnetic effect occurs. But actually, when we have studied polysilicon for thermal pressure, and we have observed that in that case, polysilicon works well than silicon. So now we are in certain dilemma and request to be sort of respectful.
Your question was not really very audible, but somehow I could understand that between silicon and polysilicon you want some discussion, is it?
Yes.
Well, when we talk about silicon, we have to keep in mind that it is its crystalline nature, which makes it handy for development of the different electronic devices, the different transistors actually. And if you want to use, if you want to actually make or grow silicon on top of oxide, it would definitely not have the same crystalline structure as we get from the crystalline silicon fabrication techniques. Okay, so how silicon is actually fabricated, that has to be kept in mind, how the silicon crystals actually grow and how then we get the wafers out of it. But if we are growing silicon, that means we are growing silicon on top of oxide to form either the polysilicon gate, or as you're talking, if we want to use it for connecting different components, then obviously it will be polycrystalline in nature. But polycrystalline materials are good as conducting lines, because if you dope them heavily, their conductivity increases and they replicate the behavior of a metallic line, and therefore we can use polycrystalline material for the formation of the gate structures instead of the metal structure. There are advantages associated with it in terms of controlling the threshold voltage of a MOS device. Threshold voltage, one of the components is the work function difference between metal and semiconductor. So instead of metal, if you use polysilicon, then that work function difference is quite negligibly small, and that makes the device actually more ideal device, or replicates more ideal characteristics, as threshold voltage of any MOS device should be as low as possible. So it is one of the techniques actually.
And ma'am, I have another question. That do you think that skin type is the reason for electromagnetic, specifically in case of internet?
I have not been able to hear you. Please, could you repeat it? The audio has not been clear.
The question is, do you think that skin effect is the reason for electron migration effect, especially in the case of interconnects?
Yeah, to an extent, skin effect also is one of the reasons, but the main problem associated it with the interconnects, particularly the metal interconnects, is the surge currents. The electrostatic discharge problem. So that occurs when suddenly the current density increases. That could be due to any reason. And if current density increases beyond the capability of the handling capability of the interconnect, then in that case the chances of electromigration shoot up.
And what are the advantages of RLCG interconnect over RLC and RC?
See, it is not the matter of it is not the matter of advantage or disadvantage. It is a method of modeling your interconnect, how you are modeling it, how you are making the electrical equivalent model. For example, if the interconnect is small, then if the interconnect is small, then you do not encounter inductive effects. So in that case, just RC equivalent model would be sufficient to handle the interconnect issues. If your interconnect is a long interconnect or a global interconnect, then obviously it will be associated with an inductive effect. You may have to take the all the four parameters which are used in a transmission line. It replicates a transmission line. Any interconnect replicates a transmission line actually. But if you use the transmission line model for an interconnect, it makes the overall analysis little complex. However, you can refer to papers by Davis Mendel and Mendel. So they have all used this transmission line model to handle interconnects. But you have to keep in mind that if the transmission line is very long, even if it is intermediate, we should go in for transmission line and distributed model configuration. If it is small, we can go in for lumped model. So lumped models of RC nature, RLC nature can be used anytime for first hand approximation of the performance, whereas transmission line model, distributed line models will give you the exact analysis.
Thank you so much, ma'am, for clearing all of our doubts.
Thank you. It is pleasure to be in touch with so many people. If any more doubts are there, you are most welcome. Yes, good afternoon.
I'm from MMT, and my question is a very silly question. If there is a crosstalk between interconnect lines,
yes,
can we reduce by creating some electric wall or magnetic wall?
Can it be?
Can we reduce crosstalk by creating magnetic wall or electric wall?
See, when we are talking of fabricating or developing an IC with millions and billions of transistors on chip, then it is not really feasible to create such type of different shields so as to protect the crosstalk. However, it is taken care of that when we are when we are making the interconnects, we keep in mind that if we keep in mind their orthogonality, that in one level if they are in longitudinal direction, the other one should be in latitudinal direction, so as to minimize the interference or the crosstalk between them to a large extent. However, it is not possible to totally eliminate these.
So, ma'am, actually, I thought if we apply same voltage, same DC voltage on two interconnect lines, then there is some electrical wall between them. Then we can we reduce crosstalk by using this method?
So you will have to try it out, research for yourself, and maybe it could be a solution in the times to come.
Thank you.
Okay. Any other question from anybody? Yes, anybody from here? Students? I hope you have studied something about this particular area. Not much.
Actually, interconnects, these are new for them.
Okay, okay. So it's always good to listen to new topics and then study about them later on. So I think if there are no questions, we can wind up the session. Once again, would like to take this opportunity to thank Shri Dr. Rajesh Mehra for having invited me here, and all the authorities of NITTTR for inviting me for this session, and to all the participants of all the institutes for listening to me patiently, and I hope you have some value addition to your knowledge. Thank you so much.
Thank you very much, ma'am, for this excellent talk on VLSI interconnects. It was really new topic for all of our students, as well as maybe it is new for our participants at different centers. So you touched upon the issues like what are the existing problems with interconnects and how they play important role in complete VLSI design. And then if anyone want to start research in interconnects, then you gave some very good information about some journals, and then very good case studies were discussed during this complete program, where some students are already doing their PhD work and they are doing remarkable job in this field. So it overall this session was really very interesting, and I hope if anyone want to start their work in the area of VLSI interconnects, so it is going to be useful for them for starting out their PhD research work or their ME research work. So overall these two sessions, and then first one was VLSI high performance VLSI design, and then VLSI interconnects, how these interconnects play a very important role in enhancing the performance of your overall VLSI design. So all those concepts are really taken up very nicely by our expert. So ma'am, we are really very thankful to you for accepting our invitation and coming here at our institute, and you have delivered these two sessions for us, for our students, as well as for our participants at different nodal centers. So it was really nice interaction with you, and you clarified all the doubts very patiently. Once again, we are really very thankful for your presence here with us. Thank you, ma'am.
Thank you so much. If you have any doubts, we can